So Yasser, over to you.
Sounds good. Thank you, Stania. I was curious actually before I start, maybe unconventionally, maybe ask you a question. What is the, I mean, the cross-modal social animation term? It's the first time I've heard this. And even though it seems to me like that's the work I am doing, like it's a type of cross-modal social animation. What is the difference between cross-modal and multimodal? If you could answer that while I set up my presentation, that'll be helpful to me.
Right. Okay, so I think cross-modal itself cross-modal is definitely multimodal for sure, but the extra aspect of cross-modal is sort of like translation. So really specifically talking about going from one modality to the other. So I think that aspect is quite important in this workshop. So just to sort of give an emphasis, I think multimodal social animation would have been great too as a title, but I think we just wanted to be more specific.
Got it. All right, thank you. All right, so let me kick things off as one. The topic of my talk is one example of an application of cross-modal social animation, and it's on telepresence. You know, what we're trying to do right now in this call is, you know, get together, discuss ideas. I think after like 18 months working from home, we'd all agree we'd much rather actually be in person, see each other's faces and interact. And that's kind of what we're attempting to do, that despite people being far away from one another, to still be able to interact as if they were in the same room. So to kick things off, I think this is a non-controversial statement that humans are social animals, right? So if I were to show you an image like this one, it's really quite astounding how much information we can instantaneously draw from an image like this. You know, I don't have to tell anyone that this woman in the background is actually not part of this social group. You know, Stephen's expression over here, Jason's facial expressions, his hand gesture over here. These are all immediately interpretable to us. Even if we don't know specifically what the topic of the conversation is, we are able to extract the tone, the feeling from it very quickly. Even it's interesting to me, we have this like slight silhouette of a person's face here. And just because we know how people are spaced, like Chaitanya was saying, we have this mental model of we expect someone to be here. And we can tell, you know, which way she's looking at. Even from the few pixels we see, we can tell that she's smiling. And this is visual. If I were to ask you to do the cross-modal translation and imagine what this room sounds like, we can all have kind of like an imagination of the buzz of a party, maybe that we remember from some years ago when we actually had parties. But yes, so we see that, we can imagine it. It's very powerful, our ability to sense this and to synthesize it in our heads. So this ability to perceive it and represent it is what the eminent anthropologist Edward Sapir referred to as an elaborate and secret code that is written nowhere, known by none, and understood by all. It's still, you know, a century later, almost a century later, this statement still remains true. There is no comprehensive dictionary or taxonomy or an understanding of the syntax or even the structure of the interactions people have. Of course, there's been a lot of very good progress, but I don't think anyone would claim that we really know this in a way that could be predictive or comprehensive about interactions and communication. So why do we care about this? So we care about this because proximity determines social relationships. This conference is an excellent example, as I was mentioning. You know, we tend to build relationships with people who we meet every day, and we tend to meet people regularly who live close by. So who lives close to you determines who you have relationships with. It's very hard to have long distance relationships, whether they're romantic or not. And you know, most of us must have experienced the case where we've either left a city or had a loved one or family or friend leave a city, and then we know what happens to relationships after that. They degrade over time. Now, we've had several kind of technological advances over the centuries, the postal service, more recently the telegraph, the telephone, which allowed, you know, at least real-time audio communication where you could hear the tone and the intonation and all of that nonverbal signal. And then most recently with video conferencing. And while this has like really been a tool that's allowed us to survive over the last 18 months, it's really limiting. About 6 or 7 months ago, I personally had a fairly big crisis of motivation. I mean, I just didn't feel like the work or the problems we were solving were very interesting anymore. And it concerned me because I didn't know whether it was the work, was I getting old, was it something else? And then we started to go back to the office maybe like 2 or 3 months ago. And within 2 days, something snapped. I suddenly felt much more motivated about the work, about the colleagues, about everything. I just felt, it was almost instantaneous. And it reinforced to me, I mean, I don't know what the exact reason for it is, but it reinforced to me the importance of all of the stuff that video conferencing doesn't capture. This is a kind of a view that's, quite apparent and familiar to all of us right now. This grid of faces. In this particular case, Mary's is talking. And it's not clear whether Salim here is actually intently paying attention to her. Is he playing Minecraft on another screen? Is Michael Finley here? Is he paying attention to her as well on a separate screen on the side? Or is he completely disinterested in looking out the window at a cat or something else? It's very hard, right? There is the sense of engagement, the sense of like sharing a space, pointing at a whiteboard, indicating attention by turning and looking at someone. All of that signal is lost, and it impacts it. There's a cognitive load. There's a feeling of exhaustion that comes from interacting in this way. So an opportunity has presented itself over the past couple of years in the form of 3D displays for artificial reality. By artificial reality, I mean virtual, augmented, and mixed reality. We've seen over the past few years various VR headsets come into the market and get adopted. And various AR glasses as well. With most recently, I think this week they announced the Magic Leap 2 as well. And what is the prospect here? What is the opportunity? The opportunity is to try to enable authentic communication, communication like you would have if you were in the same space with the other person, but in this sort of artificial reality. So to enable authentic communication in artificial reality is the task. And why this is such a challenge is actually embedded in the sentence itself. The words authentic and artificial, these are antonyms. These are opposites of one another. Authenticity is opposed to artificiality. And what we're attempting to do is defeat probably the most sensitive perception system in existence, which is humans looking at the social behavior of other humans, facial expressions, body movement, and speech. So we've seen a bunch of these social VR apps, as they're called, and all of them currently have this sort of consistent stylization, where the attempt is not to get to realistic or authentic representations, but rather these sorts of cartoon representations. And most recently, Facebook released workrooms. All of these are a lot of fun, and if you haven't tried them, I'd strongly recommend that you give them a go. In fact, this is my avatar from Workrooms. I'll just play this.
So you've been recorded. You can say something.
Salutations.
Looks good.
All right.
Okay, cool.
Yet, if you think about communication as the flow of information, the lack of expressiveness, the stylization of appearance, all of these things censor the signals that we're sending in some way. And this is an example I tend to show sometimes. This is a render using one of our avatars that we have. And if you look at this, probably I hope most of you will agree this looks like a plausible facial expression that Danny might be making. But if I show you what she was actually doing, it's this. And I'm going to flip back and forth a few times just so that you can compare the two. And even though the change is extremely subtle, the actual message that's being sent by these two, probably we'll all agree is actually significantly different. This is a sort of flat neutral expression. This slightly different expression is much more quizzical, much more querying. It's asking something. And if I and Danny were having a conversation, or if you or Danny were having a conversation, saying something with this expression means something different than this expression. And these sorts of subtleties are important to convey and communicate, and it's already hard to communicate with other people. These sorts of messages are important to preserve. And this forms sort of the basis or the thesis of the work that we do, which is that metric telepresence is sufficient for authentic communication. So let me break that down a little bit. By metric telepresence, what I mean is rather than aiming for something that looks plausible, that looks good, we try to preserve or rather reproduce to the extent possible exactly what the person looks like, acts like, and sounds like. So we want it to be indistinguishable from what they actually did, as opposed to a potentially plausible reconstruction or representation of what they're doing. And if we can accomplish that, that would be sufficient for authentic communication. In fact, my feeling is that it's stronger than that, this is necessary for authentic communication. That it'll be difficult for us to interact meaningfully with other people. Now, what does meaningfully mean? Interact with other people unless it captures the full bandwidth of communication that you want to. Obviously, there's some communication, some sorts of conversations where it's not necessary. But in my view, for like as a medium of global communication, like the phone, like messaging, like video calling, these social VR apps have to be able to produce all of that full bandwidth of communication. So here is an example of a result we showed a couple of years ago. Here I'm wearing a VR headset, so is Danny, and we've augmented it with a few cameras. This is my avatar, this is Danny's avatar, and this is a conversation we had in VR in 3D. So I'll play this and you can take a look.
Well, what can your face do? Can you show us?
Well, I've always hoped you would ask me that question.
Mm-hmm.
So I have some pretty good, I think, mouth movement.
How about your eyes? Can you look left, right, up, down? Good.
Yeah, I'm gonna be surprised. Ooh. I think one of my favorites is puffing my cheeks.
The mouthwash commercial.
And rolling my tongue.
That's pretty good, actually.
Yeah.
Good.
So we keep
not
going.
a lot of people can do that.
As you can see, obviously this is just the head, but it's kind of like a step towards this idea of social interaction as a communication network. The idea is that each person is in fact a transmitter and receiver of information, and we need to build sensor systems that can actually sense how the person is behaving, what their movements are, both visually, acoustically, and through any of the other modalities that are under consideration. We have an encoder that takes this information from these sensors and produces some sort of representation of what the person is doing, transmits this over the network to a decoder that takes that representation and produces what the display would show. And here I mean display in the general sense, not just a visual display, but microphones as well. In the future, if haptics are available, haptic displays as well. Now there's a specific kind of like interesting structure to this where the encoder, the representation of the receiver, also determines what the receiver sees. So in other words, how you appear to me depends on my behavior as well as your behavior. And I'll explain why this is true in a little bit. And then the last bit is the environment. So I'm obviously in a different place than you are. I'm lit in a different way than LP is, for instance. But we want it, if he and I were talking, that we were in the same space and it looked like we're sitting there in the same space and we're relit and resounded to sound like and look like we're in the environment together. So if we're in a cathedral, it should be reverberant. If we're outdoors, it should not, and so on and so forth. So this representation that I spoke about is what we call codec avatars. We've started this over the years. The initial one was in 2017. Improved the detail, added hair, eyes, hands, and then most recently we've gotten to full bodies, including faces, hands, and the body, background, and audio as well, which I'll talk a little bit about. So what is a codec avatar? So fundamentally, a codec avatar is a pair of functions, an encoder, FC, and a decoder, FD. And what the encoder does is it takes signals from a sensor, cameras, microphones, and so forth, IMUs, and then it transforms them into a code that represents the state of the transmitter. This is sent over the network, and then a decoder takes this representation and produces what the person would see and hear. So let's look at the decoder first. The decoder is a function that, as I said, produces what the left and right eye see, and what it takes as input is the state of the transmitter, so the transmitter's code. And it also takes the receiver's code, for a reason I will explain shortly. And finally, it's parameterized by some some variables. Of course, this function is actually multimodal. I guess cross-modal as well, but for now we'll call it multimodal. It should produce what the right and left eye see, but it should also produce what the left and right ear see. And as a input, it should also have some representation of the environment that you want to represent these people into. So this is the final form of the function. Well, one of the forms of the function, where it takes as input the transmitter's code, the receiver's code, and some representation of the environment, and displays on a 3D display the spatial video as well as the spatial audio of what the person should interpret to get a feeling of immersion in the space. And so that's kind of what we represent over here. That's this decoder bit right here. That's FD. So what does FD look like? We use a neural network which takes the code and it decodes two elements. The first one is a mesh. So this is the geometry of the avatar. And then the second is the appearance. So what we observe is that if you look at this facial expression of Shui, he's in a neutral expression. When he scrunches his face up, the blood rushes to his upper face. And so his appearance, the colors of his face, they actually depend on the expression as well. So the state of the avatar depends on appearance too. So what we do is we in fact take the same code that produces the mesh, and it also produces the texture through a different network. And so you can see this over here. This is kind of like the texture unwrapped. This is the geometry. And we'll vary these codes, and you can see how both of these change in a complementary way. And I'll play this. Now, finally, how do we train this? We train this by minimizing the error on a per pixel basis against real images. So what you're seeing here is a slider, which has a real image and the rendered image on the side. You can see it's still sliding, but it looks pretty close by. And this is actually an example of the concept of metric telepresence, that we directly minimize the difference from the real image pixels. So it's not a question of perception. Well, not a question of human perception. It's a matter of matching pixel to pixel what the camera has actually observed. And now here's where the receiver's viewpoint, where my viewpoint is important when I'm looking at LP's avatar. Why it's important is if you look at this illumination, this lobe, illumination lobe on Ian's nose, as you change your viewpoint, it actually expands into two lobes over here and then collapses back into one lobe as you go more to the edge. And this is familiar to anyone who understands graphics. The concept of a specularity depends on the viewer's direction as well. If you think about the bonnet of a shiny car in a showroom, as you move around, the specularities move around as well. Or if you think about a mirror as another good example of this. So that's why the receiver's code determines what the appearance is as well. When rendering the appearance of the person, it depends where I'm looking at them from. And so now we augment the texture network with this code of my viewpoint direction. If you note, the geometry is not affected because the geometry does not depend on where I look at it from. The geometry remains the same no matter where I look at it from. And then again, we train this network in this way. Here's an example of a result. The geometry is shared despite different views, but each of these views produces a different texture, which you see over here. And depending on visibility, the neural networks are lazy regressors, so they don't bother filling in the areas properly, which will not be seen or were not penalized during optimization. So these look perfectly right from the particular viewpoints, and they're decoded separately based on the code. So you can see over here, the geometry is shared, the appearance is different in each one. And so this is the final decoder structure, where you have a code, you have a view code, you decode the geometry, you decode the texture, you produce images, and you'll see here we'll tweak or change the view code, and then it'll produce this visual imagery. This is one view. We, in practice, of course, produce two. So you can see it's changing. Both the code and the view code is changing, and that produces this avatar that you see on the right. Now, to train this system, what we need to do is give the neural network samples that capture the entire span of the view directions and expressions. And for that, we built the system called Mugzin, which has, well, actually 170 cameras, 100 microphones, and 450 lights. And these are high resolution, high frame rate cameras. And the microphones are also very low noise floor microphones too. And all of them are synchronized to one another and timestamped. So why so many cameras? So it's because we want to actually allow a person in VR to be able to see you from any direction. And I'll play this for you to get a sense of the data that we can collect. You see from every view, the top of the head, the back of the head, and it's high enough resolution to see what Israel had for lunch that day. We built this entire pipeline to reconstruct, detect key points, do some model-free mesh tracking, personalized key points, and then finally do the decoder learning on top of that. This entire kind of pipeline takes a couple of weeks to process an individual person's avatar. You can see the annotations include the teeth, eyeballs. It's quite detailed. The result over here, again, I'm showing you the sliding view visualization, where on the left is the real image, on the right is the avatar, and it'll swipe between the two. And the white line will disappear, but it's still swiping. And hopefully it'll be difficult to tell the difference between the two if we've done this stuff right. So this is still sweeping, as you'll see over here. See, it's still sweeping, but the representation seems reasonably good. So in addition to this, we also want to represent the environment. This is something which we had mentioned. And for that, inspired by the light stage at USC, we added these point light sources all around the capture stage as well. And here you see, if I play this, now not only are we getting all views with expressions, but also with illumination changes as well. And what we can now do is, in fact, using a neural relighting formulation, similar to view and appearance conditioning, we can change the lighting of the avatar as well, which is quite exciting. If you notice the glint in the eye, it's also captured. And so here's the final form. Now we have the expression code, which we can change. We have the view code, which is your view code looking at me. And then the lighting, environment lighting code as well. That's the third input into the decoder. And what I'll do is I'll change these like individually. First, let's look at just the lighting code changing. Expression remains the same. The viewpoint remains the same. We just change the lighting. And this is programmatic through the network. Then we can change the expression and lighting together. Here, the expression is changing and the lighting as well. And then finally, we change all of them. I can look at you making any expressions under any lighting condition. That's what this enables us to do. And so I'll play this. You can see her being rendered from any environment. The compositing isn't great, but you can see it's better, much better over here. And this is a recent example. It's not exactly what was described in this paper, but close enough. So that's kind of like the breadth of this the decoder side of this network, right? So let's look at the encoder side as well. So the encoder now, if you remember, takes the signals from cameras, microphones, looking at the transmitter, and converts it into this code that then drives this decoder that we talked about. So let's look at this one. The big challenge over here is the fact that there is this, the goggles themselves occlude the face. So we really don't have an easy way to sense what the face is doing. In prior work, people actually have asymmetric experiences where only one side can see the other side. If you want to have two-way conversations, both sides need to have displays, 3D displays, which means that their heads or faces need to be covered, which is the case over here. So what we did is we added cameras to the headset. You can see there are 4 cameras over here, which I'll highlight right now. And these are the 4 views that we get. And from this patchwork, this jigsaw puzzle of the face, we need to put it together and drive the face of the avatar. And the challenge over here is, machine learning methods, even to today, they work best in the supervised regime, where you have pairs of input and output. For this input, produce that output. And you have a bunch of these. The challenge over here is that we can collect a bucket of input, lots of data from the cameras on the face. We can collect a bucket of output, lots of facial expressions recovered in Muggsy. But we don't have correspondences between these two. So this correspondence problem is what we solved using an optimization scheme, which I will describe. This is an input. And then according to our network, we can encode it to the code and then decode it to this to a particular face. And this is an initialization, which you can see is completely wrong. Her eyes are closed, her mouth is closed, but here her eyes are open and her mouth is open as well. What we do is a domain transfer, a style transfer that goes from color to IR. And then we take this and render it from the perspective of the cameras on the face. And then we adjust the code and the weights of this network to minimize the loss between the actual image and what this render produces. And as the optimization runs, you will see her facial expression change to match this particular face. So I'll show you this now. So as we play it, she closes her eyes, closes her mouth to match this expression. Let's look at another image. Mouth open, eye open, she reaches that expression as well. The next one is this kind of like angry expression. It matches it as well. Pucker face, it matches it too. To me, it's really cool to see kind of gradient descent as expressed on a face as a facial expression. There's something I think interesting about that just inherently. All right, and so here are the results of what the encoder then looks like. So here's the face. Here's the images from the different viewpoints they're observed. And we do the swipe test again. And you can see, like, it's not that this just looks good. It is actually trying to match what the person did on a pixel by pixel basis. Okay, this is a result we produced recently. It represents the state of the art of the work that we're doing. And I'll play this and you can see, evaluate for yourself where we are.
Yeah. Welcome to the Codec Avatar 2.0 demo. So let me just explain to you what you're seeing. So what this is a volumetric, reliable representation of my face, hair, shoulders, and neck. And on the headset I'm wearing, there are a few cameras observing my eyes and my mouth, and this allows me to animate my avatar in various ways. I'll just go through a few of them now. For example, I can raise and lower my eyebrows, I can squint, widen my eyes, I can look left, right, around, I can scrunch my nose, I can do various facial motions like eye, jaw motions. Yeah. Some various things. I'll do also a few composite expressions for you to judge what they look like. So I can smile, I can be angry, surprised, I can be scared, I can wink at you, and act impressed. All right.
So in my view, of course, everyone can make their judgment. In my view, this gets pretty close to realism. If anyone knows Jason or has met them, they would instantly be able to recognize this is actually what he looks like and how he moves. Yet, you know, I actually showed this result to my daughter. She's 7 years old. And I was just curious to ask her, like, does this look real to you? And she looked at it for like just half a second and she said, no, it does not. And I was very curious to like learn what was it that she picked up on that she didn't think this looked realistic. You know, what facial take or what movement didn't we get right? And I asked her, so why don't you think it's real? And she said, well, the guy has no body, very bluntly. And of course, that's right? So that's one kind of big limitation of this work, which I'll talk about in the future as a direction. Speaking of cross modality, body movement is in fact another kind of modality here as well. So anyway, this is the full loop. The encoder, it takes this input, produces a code. The code is decoded into the mesh and texture that then produces the render for the images. And I'll show you the whole machine in action right now. This is driving it. So this makes facial expressions, changes the code, which changes the appearance and the texture, which changes the facial expression, depending on which viewpoint you're looking at it from. All right. So that's the whole business. The sensor takes an input in terms of these images on the face and actually audio as well, takes the encoder, it transmits this code to the decoder, and then that gets decoded into the different views that get displayed. And this is a kind of continuous stream of exchange, right? This is information that's being exchanged continuously between the two people. Timing is very important, latency is very important, fidelity is very important. And this is another example of that sequence I showed earlier.
Have you told anybody about Yahtzee yet?
What's yacht?
That's where we build a yacht and then we collect data on a yacht.
Well, that's so clever. I like it. We should definitely do that. Now we must do that.
I think we could trademark it.
We have to. Yes.
So what's next over here, right? This is actually quite similar to the icon that Titania was showing. And I do believe, I haven't spoken about audio here as well, but that's a major area that we have to pursue. And then the full body, I talked about a little bit, that's another major area that we're pursuing as well. So let me talk about the body first. For both of bodies and for audio, we've built this capture system called the Sociopticon. And in this, you capture many views, and I'll show you what those look like.
It's a construct. It's our loading program.
Again, just like Muggsy was for the face, this is the same thing for bodies. And it has 180 cameras, but it also has almost 1,700 microphones in there as well, which I'll talk about in a second. So the pipeline for reconstruction is similar to the face one. Now we can do this reconstruction for the entire avatar. And we paid particular attention to these difficult poses. Poses where, there's a lot of self-contact. These are hard to get right. I'll play a few of them, where the hand is touching or the arms are touching the body. And of course, the arm crossed stand. This is a very typical one, very difficult to track with vision methods. And we've spent quite a bit of time trying to get this last 10% of behavior. And then once again, we have
I came across this video of this girl I went to high school with, and she's like, yeah.
So this is again another version of the same codec avatar. And if you're interested in the details, you can look at this paper we published in this year. And I'll play it, and you can see how this actually feels in VR.
Facebook, and I came across this video of this girl I went to high school with, and she's like, here's my attempt at beatboxing or whatever. And there's like 3 people. I didn't know who the other 2 were, but there was like one.
Facial expressions, hand movements, but that was a playback. This is the last result I show for bodies. You can see Vasu's wearing a headset, Autumn is wearing a headset, and they're interacting, and Vasu's seeing Autumn in VR. What you're seeing over here is what Vasu actually sees. Her face, her hand, the body in the background, and audio actually, all of it rendered in real time in VR. And I'll play this for you now.
Yeah, so Autumn, I hear you are starting a new yoga class. What's that like?
Oh yeah, my new yoga class. So I take some yoga classes, right? And I am really trying to so they have the warrior pose, right? Where you're supposed to do that thing, right?
Nice.
And I can't get my feet position right ever.
So the only input to produce this are those 3 images for the face and the stereo pair for the body. Right now, this is an early result, and it works with a predefined model of Autumn, and it only works in this particular location. But that's the start. We're going to work to generalize it from here in the future. The final thing I'll talk about is the audio system and what we're trying to pursue over there. So in the Sociopticon, there are, in fact, this is the correct number, 1760 audio channels, where they are in the form of these tetramics. These are ambisonic microphones that are on the surface of this dome. And what we can do with this is, in addition to reconstruct the avatar, for the first time, we can also reconstruct simultaneously with a detailed avatar in there, the sound field as well. In other words, what the pressure is at every location in the space. What you see here is this yellow dot is a virtual microphone. So if your ear was there, it can generate the sounds you should hear. And as you move around, we can generate what you should be hearing from your left and right ear to give you a sense of immersion. And this is the signal from that yellow microphone that we simulate. So let me play this for you as well.
This is a construct. It's our loading program. We can load anything from clothing to equipment, weapons, training simulation, anything.
So you see he snaps his finger, and what the system is able to do is actually see how from this kind of impulse function a wave emanates out. See that, like there's this wave, we can slow motion it. We can also do a kind of like frequency sweep and look at the different frequencies at a particular time instant. One thing that interests me a lot, because I show this video quite often, is that when you snap your fingers, in fact, there are 2 waves that emanate. One is outwards away from the body. The other one is back in towards the person themselves, and it bounces off, it gets reflected off the chest of the person here. And in fact, what's really interesting is you see it captured. There's the primary wave over here, but then there's a secondary wave coming out over here that's interfering with the primary one as well. So it's, to me, very cool that this managed to catch that without any prior or actually trying to model this effect.
we need. Is it really so hard to believe?
So there's a phone in his back pocket that started, and so it's also sort of capturing that that effect on his back. So you can see it's emanating from his back pocket.
How do you define we? If you are talking.
So you can also slice this because obviously this is a full three-dimensional volume in there as well. All right. What we're pursuing is just like we have a codec avatar pipeline that uses neural rendering methods visually. We've also done the first work or some of the first work in neural rendering for audio as well, for spatial audio. And this is an example of the blue is the actual recorded video held out. And the orange is in fact the codec audio prediction of what a microphone would look like in a particular location. I'm just giving you this as an example result without going into the approach or method, but there's a paper that we published this year on it. If you're interested, I can share that with you as well. And this is compared to classic spatial audio methods. And you can see here the DSP method in red is significantly different from the inaccuracy from the version that we can get in codec audio. And I'll show you a final demonstration of this. So this is a rendering of this codec audio, which is conditioned on where the speaker is, where the listener is facing. So here, Hirsch is going to wear the headset. I'll let him explain actually.
The position of the avatar is going to be controlled by an optics controller that my mom has graciously wanted to move around the scene. I'll be playing the role of the listener with my headset. And during the second half of this demo, I'll attempt to localize the position of the transmitter using only the audio stream. So let's get started.
So what she's going to do is she's going to be walking around, and he will sort of like face her because he can't see her obviously. Just based on what he's listening, he will face where he thinks she is in the real world.
Take charge of choosing her bridesmaids' gowns. A voice book near at hand.
So the controller actually moves this pre-recording of Alex in 3D space. We transform it to produce the audio on the left and right here, which Hirsch can't see. So then all he's doing is following what his ears tell him where this controller should be.
It's left their thighs. It's healthier to cook without sugar. You'll change your shoes before you turn around. Cliff was soothed by the luxurious massage.
So now this is the second part where he'll just point to where he thinks she is.
Eyes might roll. Thank you, she said, dusting herself off. Why charge money for such garbage?
So this demo was built using what we call hearsay. This is the final capture system I'll talk about. It's in essence a room full of ears. And in each of these ears is in fact a microphone. So it has 192 microphones spread around the space. And we've captured people moving around speaking while wearing the headset in there as well, which allowed this kind of a result. So I'll play this a little bit so you can see what that looks like. That music is a bit dramatic, but you get the picture of what this shows. Right. I'll conclude with that and just say, obviously, this is work by an extraordinary group of people. I'm just presenting the work. And I really look forward to the next phase of this work, which is in essence the topic of this workshop, which is how do we now to start to fuse audio and video? How do we use the audio input microphones on the headset to get better definition of what the mouth is doing? How do we use the behavior of the person? You know, am I covering my ear? Am I sort of like facing downwards? How does that change what I hear? You know, these cross-modal interactions are critical along with the third one, which is the environment. How does the environment change how I look in terms of lighting? How does the environment change how I hear the audio as well? These are very interesting and important problems that we have to solve. And I'm convinced that, you know, our perception system is multimodal. It is, you know, it is fusive. When we have two cues that tell us something is true, our brain tends to snap and believe it. And I really look forward to us getting to a point both visually and acoustically where it is fully realistic. And so when you look at it, you get that sense of immersion and feel like you're sharing a space with another person. This is a collection of papers that we published, but I'm happy to answer questions. If you have any, that's my email address at the bottom. Thank you.
Thank you, Yasser. That was amazing. I think I remember meeting you for the first time at Facebook Reality Labs, and I think it took you like 10 minutes to explain what was going on in the lab. And I was like, oh, this is amazing. And I think I had the same feeling today, like seeing how it has progressed over the last few years. Thank you. So if anyone has questions, please feel free to unmute and ask the question, or I'm also keeping a track on the chat. So. Right. So, Rich, go ahead.
Is it okay? It's obviously hugely impressive, and it's going to be a difficult app to follow. But the models that you're building at the moment, they seem there's an awful lot of curation that goes into the models. And I'm just wondering, so obviously all of the subjects, the models exist. You have the opportunity to optimize the algorithms. I mean, in order to get this into living rooms where somebody just puts the headset on and there's no kind of how do you solve that problem? Getting this to work for anybody without the huge kind of effort that goes into the model building.
Yeah, that's an excellent question, and I think I'll underline that twice. If the expectation is that people come into these scary-looking capture systems and have to spend an hour and a half to get captured before they get an avatar, that's just a non-starter. It's not. I mean, that's not something which we will ever see. People adopt at any sort of scale. Maybe at some small scale, but not at a serious scale like we want to. So our approach to this is that we've started what we're calling the Universal Avatars program, which is we want it to be as easy as a quick scan with a phone, plus some facial expressions that you make. That should be enough for a neural network to actually produce your codec avatar from. To do that, we have to actually produce avatars for a large number of people. We actually have to go and get that sample set, which we're beginning to populate right now. The challenge is it's unclear how many people are in fact needed, because even to this date, people's understanding of diversity is actually kind of primitive. It's not just about ethnicity. It's not just about kind of appearance. It's even about how you move, how you sound. Those sorts of things matter a lot as well. And there's not a kind of like a clear understanding of this. So we are planning to start to build this kind of corpus and then explore the space. We have some early results which are looking promising, but tell us as well that the 3D shape or structure, that's easy to span, that we can get with a few hundred people. Appearance and motion, that's something which has a very long tail. That's going to take us a long time to build up. One interesting early insight is that audio is a strong correlate with facial structure and movement. So how you sound actually, I mean, this is known physiologically, depends on your face structure as well. So once again, this theme of cross-modality comes back in. These are all intrinsically related to one another. So if we had a quick scan where you spoke as well, and you had a quick scan of your structure, and you made a few facial expressions, the hope is that there's enough in there to infer what your avatar looks like. But that's a big if, and that's what we're trying to prove out now.
Thank you.
Yeah, I had one question. Yeah, can I go ahead?
Yes, please.
Yeah, all right. Yeah, thanks, Yasser. It was a really amazing talk, and so you have really pushed the limits of what you can get pixel perfect image and really wave perfect audio. So it's really high fidelity. So I was thinking about now you sort of have to find out how you can compress all of this or kind of downscale it, if you will, to a point where you don't have to do all of this work, but still get the right message across, still get the right expression, so still get the things that matter to the end users. So what are you doing maybe in terms of evaluation or perceptual studies or something like that to figure out what are the essential parts that you can't leave out, and what are the non-essential parts that you could possibly cut or kind of cut down on or compress?
Right. So I'll make two statements on this. The first one is factual about what we're doing. The second one is a little bit controversial, but I hope in the spirit of discussion, it'll be interesting to some. So the concept of a codec avatar, where we have this encoder and the decoder, it naturally, in fact, compresses the code. So the representation that we have is 128 floats. So this is like tens of kilobytes per second. It's already quite compressed. And now this doesn't include audio, but that would also be quite small because it naturally compresses the data and sends it. And as a scientist, I find this like very satisfying. Like we had the bottleneck in there to encourage learning, but the structure is such it's exactly right for compression and transmission. So it's inherently compressed, and it's compressed with the intent of reproducing the pixels. So that's hopefully the uncontroversial part. The controversial part is on what should we evaluate. And I think there are two ways of thinking about this. The first one is we need to identify perceptually what's important to people and try to optimize the compression for that. And I think this is very reasonable. The counterpoint, which is my perspective, is if you ask a cognitive psychologist, most perception is in fact unconscious. You're not aware of what you're perceiving. The conscious part of perception is a very thin layer on top of that. And what is important in aggregate might change depending on the context of the conversation. So if I took like an hour, 2 hours of conversation with you and said to you, and then we tried to do an analysis of what the important parts were, I think it'll come out. The eyes are important, the mouth is important. But perhaps there is a conversation in which my nose twitch is important, suddenly, right? Just in the context of that. Am I talking about allergies or something? Then suddenly something else became important. It changes according to the context of the conversation. That's number one. And second, we really don't have any means of directly querying the unconscious parts of our perceptual system to quantify what is or is not important. If we could do it, I'd be supportive. But so far, I've engaged with, read a lot of literature. I've not found a good way to quantify that, quantify the unconscious part of perception, which is the majority of it, and also find a way of quantifying what is important depending on the context of that conversation. Okay, so that's one part. Instead of that, in my view, what we should be doing is taking the sensor data and saying, let's not bias towards what we may find from a partial study or a partial analysis of what is conscious and what is not, and instead just try to reproduce what the pixels of the camera see. Pixels don't lie. The audio doesn't lie. If we can reproduce all of that properly, then that is sufficient to produce what is important perceptually as well. However, because of our partial understanding of what is perceptually important, satisfying that does not guarantee that we're capturing all of what is important. So in my view, our approach should be, let's try to reproduce what the sensors see to the full fidelity. But I mean, this is of course my hypothesis. We'll see what comes out from the research as we go forward.
Thanks.
Thank you, Professor, for the amazing talk. It was really inspiring to see like what the state of the art of the field was. And it was super inspiring for me as a student in this field. One question that I had was, in a lot of these cases that you explained earlier, it seemed as that you're using acoustics as a sole modality to reconstruct a lot of these, I guess, facial features or, I guess, bodily gestures and et cetera. But I guess from literature, we know that language is a good predictor of facial expression as well as hand gestures. So I want to hear your insight as to, I guess, what your insight was in terms of incorporating language features in terms of reconstructing all of these features that you mentioned in this talk.
Do you mean language features or speech features?
I was talking about language.
Yeah, that's very interesting. I mean, I find this entire area, I mean, we've certainly not explored it fully. And right now I'm just talking about speech, not even getting to language, right? Speech, how speech informs facial expressions, body movement, it certainly contains information. I think the part where language is very interesting is one of the ways in which this interaction even is different from a real interaction is latency. You know, like even though it's kind of, once again, that imperceptible thing. Perceptually, we can tell when it's about 120 milliseconds, but subconsciously, it's likely, this bears intuition. It's affecting our conversation, the lack of instantaneous response. We're interpreting that in some way. And that will be just as true in VR as it will be for VC, except for prediction. Like if we can forecast a little bit out, 10 milliseconds, 20 milliseconds out. And my sense is that the language models or a higher abstraction of interpretation will help us predict further out more accurately. This is again a speculation, but my feeling is that's the role where language will play a critical part, allowing us to do some social prediction, and by accomplishing that, allowing us to reduce the apparent latency in these conversations. That's the promise of it. From my perspective, that's one at least very high value that this could provide.
So just a follow-up question then, do you think that acoustics is enough in terms of, I guess, how, like, let's say that you want a very fine-grained expression that really exactly, because we initially saw that there was like minute differences in the generation versus the actual like facial expressions of the speaker. Like, I guess my hypothesis from just hearing this talk is that like having a semantic understanding of the language should be able to inform the model to have, I guess, more finer, be able to be indicative, I guess, more finer expressions. And was that not the case, or is acoustics just enough?
Yeah, so the stuff that we're generating from are images. My sense is acoustics and even language, certainly not, and even acoustics are not sufficient to reproduce facial expression. They're only sufficient to produce like mouth movements and perhaps some residual correlated movements as well. But where their value is in terms of their complementary information. Like there is a lot of important information in there, which is complementary to the visual cue. I don't think we should be thinking about this as one modality or the other modality. We should be using all of the modalities simultaneously. And there's so many interesting research problems in this. Audio comes in at a much higher sample rate than video does. It is low dimension compared to video, which is high dimension. So there's so many kind of like complementary aspects of this on how you'd model it, how you'd use it for prediction. I mean, we have some good work, early work by, for instance, Titania and LP, but this is just the beginning of the field. There's a lot of work ahead.
Thank you so much.
I think we are out of time for this. Thank you, Yasser, again. This is really an amazing talk. And now we can move on to Richard. So Richard, if you want to share your screen.
See, of course, when I do that, it completely ruins my setup. Can you see the slides?
Yes, yes. Yeah, so just a quick introduction about Richard. Richard is a professor of computer vision and machine learning at the University of Surrey, where he leads the cognitive vision group with a center of vision, speech, and signal processing. A lot of interesting research on the use of computer vision to locate, track, and understand humans have originated from this group. And personally, I've enjoyed reading his work on sign language production. And sign language is purely a visual modality, but it is heavily driven by text. And that text modality represents the semantics of the communication. And I'm really excited to see what he has in store for us today. With that, over to you, Richard.
Well, thank you very much for the nice intro and for the invite. And I apologize, I've had a stinking cold all week, so I don't normally sound like this. And if my voice goes or I start sneezing in the middle, you have to apologize. And so, Yasser, that is a really difficult talk to follow. But I don't know, it makes me very excited actually, because I think, I mean, if you can put some of the technology that you're developing together with some of the things that I'm going to talk about here, or we're still trying to solve, then I think the future is very exciting. So I kind of guessed that you wanted me to talk about sign. So that's what I'm going to focus on today. Just in terms of a bit of an overview, I'm going to say a little bit about myself, because I work on the assumption that nobody knows who the hell I am. I'm going to talk a bit about sign language, some of the current projects in sign. I'm not going to really dwell on the older stuff, but some of the tools that are currently under development. I'm going to spend a bit of time making a very clear distinction between translation and recognition. And I think there's been a shift in the field lately, where we kind of moved over to, we've all moved neural network anyway, but over to more the neural, NMT stuff, the neural machine translation techniques. And we've started doing some production as well, although what I'm producing doesn't look anywhere near as good as Yasser's avatar. So obviously we've still got some work to do. So who am I? So as you said, I'm a Professor of Computer Vision and Machine Learning at the University of Surrey. This is the last photo I had of the kind of group before we went into lockdown. So quite a few of these people have left now, and I think we've had about 4 new people who've started PhDs completely remotely, which is a strange, strange experience, but we are gradually going back to the lab. It's funny, somebody said before about product, it was Yasser, wasn't it, sort of saying about being back in the lab and getting his enthusiasm back. I think productivity's been up while we've all been working remotely. And even the people in the group kind of say this because, well, I couldn't go to the gym, so I might as well work instead. So I think productivity is going to go down as we all return, but hopefully mental health will go back up again. You can tell which one I am because I'm the old one. And like I say, so I lead this cognitive vision lab and it's one of the labs within CVSSP. So CVSSP is pretty big. In fact, I lose track how many of us there are. We're broken into these little labs, and the cognitive vision lab, which is the one I run, has 2 main funding streams. So we do some fundamental stuff, which is more on the kind of fundamental computer vision, but we focus on robotics, autonomous systems, and sign language and recognition and translation. So this is me in a slightly different guise in the robot lab. We've got our little autonomous test bed, which is a Twizy that I have hot-wired with a NVIDIA PX2 in, a LiDAR and some cameras. And we're using this to do things like feature learning that overcomes kind of day, night, or environmental factors. And some more recent work that we've been doing on BV, bird's eye view estimation directly from cameras. But today, like I say, I'm going to be focusing on the sign language work. And what I want to start with is really just to dispel some myths. So I'm sure, you worry about teaching people to suck eggs, but also I think there's an awful lot of misunderstanding. And certainly computer vision has tended to look at sign language and just go, oh, it's just gesture recognition. And it's not. I mean, it is a full language in its own right. It's as rich as any spoken language linguistically. And so I just wanted to go through some of these points. So like I say, it's a visual language. It's the native language of deaf communities. And it's important to note that it's the first and primary language for most deaf. And for various reasons, largely historic, it might be that actually their command of written or spoken language is actually not that good. So in the UK, I mean, and that goes back historically, the education system, I think, has failed some of these deaf communities. And so it's not just a case of, oh, well, can't they just read the subtitles? I mean, subtitles are a written form of spoken language, and the sign language of a country is a completely different language in itself. It's not just a visual representation of that written word. Another thing that often surprises people is that every country has its own sign language. So there isn't just one. What? There isn't just a single sign language? And that's like saying, what? Well, why isn't there just one common spoken language? Language evolves, doesn't it? And it evolves from communities. So it's quite natural that that each country has its own sign language in the same way it has its own spoken language, but even regional dialects. So the lexicon in the north of England is completely different to the lexicon in the south of England. There's different signs for different words. The grammar and the structures of the language might be the same, but the lexicons are completely different. And to be fluent in BSL, in theory, you are expected to know all of these regional dialect differences. There is no simple mapping from spoken language to sign. They've got different grammatical rules and linguistic structures. And actually, there are linguistic structures in sign that really don't have an analogy in spoken language. And I can give you some examples. I mean, there are complexities which even now we completely ignore when we're talking about automatic translation. Things like placement. So space is used in sign, and space is used both kind of topologically and syntactically. So if I was talking about geography, then I might be using the space in front of me to reflect that geography, but I can also place objects. So, maybe I stick America over here, and I live over here. And then I could sort of say, I fly to America, or, I sail over in a boat. And so these verbs become directional between objects that I've placed in space. Conversations as well. I can put people in space, and then I can use something called role shift or constructive action with a slight turn of the body to say, well, he said this, and he said this, and he said this. So and there's all these things that at the moment, in terms of computational approaches, we ignore. I mean, we're still sort of where speech recognition was decades ago. Now, everyone knows that sign uses hands, which we would turn the manual components, but it also uses the non-manual features. And I think we've just been hearing, we take it for granted that the face, these other communication channels are an integral part. And that's equally true in sign. So if I give you an example, this means far. This is the citation form for far in BSL. But if I go and place emphasis on it, that means it's a long way. If I really labour, it's a really, really long way. If I kind of give it a little head nod and an eyebrow raise, then I'm asking a question, how far is it? And then another thing is, and actually sign is getting really popular at the moment. It used to feel like nobody really cared. Everyone thought it was just, it's just like gesture recognition, it's easy. And all of a sudden, I think the technology is caught up and it's allowing us to do much more impressive things. And everybody wants to solve sign language. Yes, because it'll help the poor deaf people. But actually, what we tend to do is just annoy the deaf communities by doing it without them. And I think if anybody wants to work in this area, then the first thing you should do is go and learn how to sign and learn something about deaf culture, and then find some good deaf collaborators to work with. Because at the moment, we seem to be creating this huge barrier between what we're doing and the people that in theory you're trying to do it for, because we're not working together. And I think the last point, which is part of that deaf culture, deaf people do not see themselves as disabled. They are fiercely proud to be deaf, and really they're part of it's a minority, it's a linguistic minority, but they're very proud of this language. So we need to do things with them. And then I just want to say a little bit about some of our current projects. So, for instance, we've got Extol, and this is a UK-funded project, and this is collaboration. I've had a long-standing collaboration with Andrew Zissman's group at Oxford, and so this is our second project working on BSL. So there's us, there's University of Oxford, and there's also DECAL at UCL, which are the linguistic partners. Trying to sort of like best practice, we have deaf team members and also deaf advisory board members. So we're trying to do this in collaboration with those deaf communities. And this project has two main objectives. So the first one is about linguistic annotation tools. I'm going to talk, it's going to come back about this kind of the linguistic annotation and the study of sign, and how labor intensive it is for annotators to go in and annotate this data. But obviously, from a machine learning point of view, I would just love to have lots of annotated data to throw at machine learning. So there's a partnership here where if we can provide some of the tools to help them annotate the data, then in return, we get back high quality data for doing our learning. And so it's about this tool development, but then ultimately it's also about trying to build systems that can translate BSL into spoken English. We've got Smile 1 and Smile 2. Smile 1 is finished. Smile 2 started in January, and this is a project funded by the Swiss National Science Foundation. IDIAC's the lead. We've got University of Zurich as well, and HFH in Zurich. And this project is more about language learning. So it's non-native signers who are learning to sign. Can we provide tools to help them and assess their language learning skills? And then finally, we've got Easier, which we started back in January as well. And this is a hugely ambitious EU project that hopes to translate between different sign languages and spoken languages. And what this has done is it's brought together most of the linguistic partners across Europe to try and pool the annotated data that there is available out there. And then we're also hoping to bolster that with less structured data from broadcast. But that comes with its own issues. So what core technology and development? Well, I sort of said, one of those projects, Extol, Smile is about assessment. So this is actually a very simple system we built during Smile 1, which was really just about lexicon learning. So designed for somebody who's learning sign for the first time, the user's asked to perform a sign, and they can be prompted either with a video, which means that it's a reproduction system. So how well are they reproducing a sign? Or they're given the gloss or the English word, and then it becomes a memory test. They perform the sign. Back then we were using Connect, but obviously technology's moved on now. And then we're just doing some analysis to try and compare their sign production against a library sign from a native deaf signer. Anywhere where we spot any discrepancies, feedback can be given to the learner. So you can see here it's highlighting that there's a problem with the hand shape. And then we kind of gamified this so that somebody could sit there and do a little test, do it, like I say, as a memory test or as a production test, and then they get a score at the end. Video's a bit slow. You get a score and you get this little feedback form. And if you click on any of these little ticks or crosses, then it takes you to that feedback screen and shows you where it was. Was it your timing? Was it your hand shape that was wrong? So Smile 1 was, I don't know, it focused on isolated, and I never really liked that because it meant we couldn't look at the non-manuals. As I said before, it's so much of sign. So much of the information content is actually in the facial expression and these other channels. So it's important that we look at it. The trouble is that in isolated sign, there tends to not be that many non-manuals. It's really only when you start continuous production that these multiple articulators come into play. We've also been developing tools for annotation. So, I mean, this is some work by Phil from the lab a couple of years ago, where we were just doing hand tracking using a Connect camera in real time. The problem is that the data that we're working with doesn't look like this, right? So the data that we're working with looks like this and was probably captured 15 years ago on a VHS recorder, because the linguists have already spent sort of like thousands of hours annotating it. They can't just go out and capture new data and start annotating again. So the tools that we're trying to develop have to work with data that is far from ideal from our perspective. It's low resolution. Sometimes it is VHS video that has subsequently been transcribed onto a digital system. Lots of motion blur, very poor lighting, because they're not computer scientists. They didn't really think about even lighting the subject, or the fact that actually, if they didn't light it correctly, that was just going to make the motion blur artifacts even worse. But the reason this data is so valuable is because this is Elan. This is an annotation tool. There's a couple of popular ones out there. Elan and Ilex are probably the two of the more popular. But the linguists spend most of their time going through this video and then basically hand annotating that said, between here and here is this sign. And this sign consists of these aspects. And the truth of the matter is those non-manuals, the things that actually I'm really keen that we use more, don't get annotated very much, because it's so expensive for them to annotate the data at the gloss level that they never get around to it. And so maybe I should now, no, I'll come back to glosses, right? So what we want is to be able to, for instance, recognize these hand shapes in these very poor quality. And this is a tool we've generated just for the linguists to help them annotate. So here you've got a selection of videos. Here we've got a little window that shows them what that video is, so they can see the hand shape in context. And this is actually part of the problem. There's huge discrepancies between what is actually going on and what the annotator annotates, because they don't annotate what they see. They annotate what the person was meant to do based on the context. And that introduces all sorts of problems for machine learning, because if it's actually it's this hand shape, but they know in the context of the sign that actually it should have been this hand shape. They will automatically kind of say, oh, well, it's this one. I know they're trying to do this one. It was just that they didn't. And so they annotate this data. And then what we end up with is corrupt data that we're going to then start putting into the machine learning. So you've got all of these issues about the fact that the annotator is not actually, strictly speaking, just annotating what they see. They're annotating what the person intended to do based on the context that it's been done in. But we give them the context, and then we're also giving them basically a ranked list of the output from a classifier. This is just a pretty deep CNN that's making some decision. And by giving them a ranked list, this means that that it doesn't have to be 100% accurate in order for it to be useful for the annotator. It just means that what we're doing is aiding them in this annotation by the system having a bit of a guess about what it thinks it is, and then allowing the user to correct that. And then as the annotator is doing this annotation, we're adding that data back into the machine learning to improve the models. We've also been doing some work on skeletal estimation. I sort of said, you know, in that SMILE project, we used Connect. We now use things like OpenPose and MediaPipe. The problem is that a lot of the pose estimation algorithms are not really developed for sign. They're developed to give a pose estimation of anybody in any image. And the failure cases tend to be hand-to-face and hand-to-hand interaction. So once you start doing this with your fingers, then a lot of the body pose estimation techniques start to fail. Also, fast motion and motion blur. And unfortunately, the hands in sign move pretty quickly. So what we do see is that even the state-of-the-art pose estimation tends to start to break down in the context of sign. So this is some work that we did, basically building a sign BERT. So we can train it to try and correct some of these failure cases in a self-supervised way. And then we're also been working on sign recognition spotting. And this is primarily because I said before, we've got annotated data, and the first thing that the annotators would do is the glossing. Well, actually, if we could automate that process for them, it would make it easier. But we also want to align some of this broadcast data. So being able to spot signs is very important. So this is a technique that that we will be publishing very soon. It's been accepted, but we're just using i3D features and then a transformer architecture to basically try and find signs from a dictionary which are isolated in a continuous stream. And so we have to train it up for the data sets, but then this means we can get results like this. So here you can see this is on the left, the query comes from the BSL sign dictionary. And then on the right, this is their linguistic data. And we're just running through, and you can see the red is where the annotator has said the ground truth sign actually is. And the green is the output from the classifier, just where it predicting where these signs are. So tools like this, all of these tools, the handshake tool and the sign spotter, we're hoping to release to the linguistic community, to the wider linguistic community this year to help them annotate more data. Okay, now I said I wanted to make a bit of a distinction between recognition versus translation. And part of the reason for that was that what we were just looking at, this idea of recognizing a sign is isolated sign recognition. And we've kind of moved on now. A lot of the data sets were, in fact, I mean, Challearn this year had a competition which was isolated sign recognition. But it's not the problem that we're really trying to solve. And over the last few years, we've moved to this idea of translation. So just historically, I mean, when we started working on this, we did tackle it very much from an isolated recognition point of view. And this was back in 2004. And then we turned to the sign linguists. We sort of said, well, how do you represent these things? And we kind of had this two-stage classification. So first of all, we would track the body, then we would extract features that the linguist would say were important. So, you know, they represent, when they describe signs, it's about, oh, your hand is in contact with your body and it touches the side of your face and it has this hand shape and things like that. So we would describe the sign at that level, and then we would have basically a temporal classifier that would look at how these features evolved over time. And sort of like last, 2004 to 2010, we really focused on those manual components. We looked at lots of different ways of doing it. And it was only really Oscar Collett in about 2014 where we started to look at what was going on elsewhere in the body. And we started with mouthings. And I said before that the sign linguists tend not to annotate non-manual features because it's just so expensive to do. But mouthings are something different. Now, a mouthing, you've got things that go on around the mouth during sign. You've got mouth gestures and mouthings. So a mouth gesture would be something like, right? So kind of a cheek puff, like that. And that's the BSL sign for easy. And so, that's a mouth gesture and it's a constituent component of a sign. But a mouthing is where I mouth some visemes on the lips that go with the sign. And a good example might be mountain. So, you might have the manual component of a mountain. But if the difference between the signs, if I was going to say mountain and Alps, it would be the same manual components, but it would vary with what I put on the lips. And so these mouthings tend to be artifacts of that come from the spoken language, but they're also extremely variable because if you're a deaf signer, then what you mouth is kind of the minimal content that you need for another deaf participant or deaf signer to understand the difference between mountain and Alp, for instance. But if you're a hearing signer, then it's highly likely that that it's coming from the original world. So it's much more likely that you're going to mouth the whole of the word. So hearing signer tends to mouth more than a deaf signer. So there's these differences. But Oscar, back in 2014, we basically used a forced alignment approach. So we could have variants on, we know which signs there is likely to be mouthing to go with, and we've got these pronunciations. So, you can sort of say, well, it might be no mouthing, or it might be A, it might be AL, it might be ALP, maybe ALPS. And we basically used the forced alignment approach then to annotate the data and train up a classifier. But initially, it was based on AAMs. But then in 2015, when we all started going a bit deep learning mad, we moved to CNNs. And that's actually when it all changed, really. We used that same forced alignment approach in Oscar's 2016 paper to do forced alignment for hand shapes. And that got us this 1 million hands classifier. And that was actually the first classifier that then went into that hand shape analyzer. And subsequently, we've been improving it with more linguistic annotation. But the important thing is kind of from this point, it all became deep from then on. So this is that first hand shape analyzer, that 1 million hand CNN, and you can sort of see straight away, I mean, it's not perfect, but it's very good. And this is working on the Phoenix data set, and this is just some random video taken off the web. Then Jihan started to look at other ways to do it, because the forced alignment, we were effectively sandwiching together sort of like HMM technology with CNNs. And I mean, it's been done, hybrid or tandem approaches, but we started to look at the sequence-to-sequence learning. So in 2017, we published subunits, and this was really just using a CTC loss to overcome the fact that we didn't have the alignment. So it's so somewhere in there is the signal. But what this did is it opened the gateway for us to tackle translation. And it was that move to sequence models. And this just kind of reiterates what I'm saying. So here what we've got is a video of sign, and here what we've got is the sequence of glosses. So if I was a linguist and I was going to go in, I would say, right, well, they signed this, followed by this, followed by this, followed by this. And this is the German or English translation of that sequence. You can see that actually the ordering is different. So it really is a translation problem to go from the signed video to a spoken language equivalent. But the other thing to bear in mind is that, as I've said, this gloss representation doesn't contain anywhere near enough information to go directly to this translation, because all of the non-manuals are missing. You know, in that example I gave you with far, the cheek puff or the eyebrow raise was what was, you know, taking that one sign and saying it's a long way, it's a really long way, or turning it into a question. And none of that information is contained in this gloss. So while this gloss is very useful, it's also, it doesn't contain enough information if we want to translate via it. But then in 2018, so Gian, we published our first kind of neural sign translation paper. So first time we weren't just doing recognition, and we just had an encoder decoder network. And this was great, but we were going via this gloss representation. And so in 2020, when we moved to transformers, what we did is we decoupled this, this reliance on gloss. So instead, you know, we still got our CNN backbone, we've got our transformer network, but we added in the gloss information rather than forcing the classification to go via a gloss representation and therefore effectively throwing information away. We could just add this in with the CTC loss to give us a boost. And this kind of conditions the network joined learning, but we're not limited to it. The problem actually we've got now at the moment is, and this is, right, well, I'll be honest with you. You know what it's like. There's a data set out there and everybody is trying to get the highest number they can on that data set. So, and what everybody chooses to ignore is the fact that all they're actually doing is overfitting to that data set. So I've got some real difficult conversations in future papers where I've got to start convincing reviewers that they need to stop focusing on performance on Phoenix, because the Phoenix data set, which was very instrumental to push the field forward because it's got quite a small domain of discourse. It's just too small a data set, and nothing that you train on that data set is going to generalize out anywhere else. So certainly the backbones are overfitting, and the domain of discourse is too small. And I'm going to come back to this, but we need to start basically expanding to much, much larger data sets. But that's going to mean that performance is going to take a massive hit as well, as we do. Where we currently are is with this architecture is Gian basically has come up with a multi-channel version where we can take some of those inductive priors that we had very early on about, you know, that come from linguistics. We know it's to do with the face, we know it's to do with the hands, and basically break these channels apart and put them back together as part of the attention mechanism. That gives us, again, a performance increase. And there's just some examples here of, these are examples from the Phoenix data. So this is the original sign sequence, and you've got the ground truth, and then you've got the output of the NMT network, and it's pretty close to the ground truth. But like I say, I mean, this is great, and it was a brilliant data set for moving forward, but this is a very small domain of discourse, weather. It's also, from a deaf point of view, a completely pointless corpus. I mean, why on earth would they want a translation system for weather? You know, I can look at the map. I don't need a translation system for. But the reason why it was so important was to make small domains of discourse. And now what we need to be doing is building it back up. But the problem is, if you turn to the linguistic data, the domains of discourse are so general, it's just open conversation, that we haven't got enough data to scale to that complexity yet. So we need some middle ground to tackle these things. So next, I just want to say a bit about sign production. Now, I always shied away from sign production, and by which I mean generating a signing avatar, for want of a better word, from spoken language, because it has always been so poorly received by the deaf community. Quite right. You know, whenever you look at this technology, it looks like a very robotic kind of graphics avatar. You know, with if the avatars look like the stuff that Yasser was showing, then they would be over the moon. But you know, we've still got an awful lot of technology we need to do, you know, in terms of the translation to get to the stage where we can get that level of realism. Because it doesn't matter if the avatar looks good, if the animation is jerky, then it's all the uncanny valley, isn't it? So I've always shied away from the avatars until we started playing again with these NMT algorithms. So we started to look at whether we could take NMT, which traditionally is like symbolic, symbol to symbol, language to language, and whether we could actually turn this on its head and translate from language to skeletons. And we came up with this progressive transformer approach, which we published last year. And I'll just show you some examples. I mean, really what we've got is a transformer NMT architecture with a regression layer on the output. And so it's regressing directly to skeletons. And then we have this counter that allows us to drive the animation. And you can see on these videos, we've got the original video. We've got, on the right, we've got a skeleton that's been extracted from that video via OpenPose. And then in the middle, we've got what the NMT system is predicting. And it's predicting, quite close skeletons to the original animations. The problem is that there isn't enough really information in this skeleton for it to be understandable. I mean, and if I show this to a deaf person, they'll go, well, that's not a person signing, it's just a skeleton. So somehow I've now got to get from this skeletal representation to an avatar that looks like what Yasser was showing. And that in itself is non-trivial. But the way we've been going is with GANs. So the skeletons, I know, those skeletons are not perfect. But we got quite excited by this because this was the first time we'd really taught an end-to-end system to go straight from the language to motion. And although these skeletons, they still need an awful lot of work, the next question was, could we animate from the skeleton to something that looked photorealistic? And that's where we turned to GANs, and we've got this system called vSign, which is basically just a photorealistic sign language video generation system. It's not perfect. Again, it's work in progress, but it's all 2D. So this is a difficult gig to follow Yasser with his lovely avatars. But maybe I'll just show you what it looks like. So this is Barbara. Barbara is a native DSGS signer, which is Swiss-German sign. And what we've done is we've extracted this little skeletal animation from the original video, and then the GAN is conditioned on this skeleton. So what we're doing is generating this directly from the skeleton. And it's not perfect, but the deaf community have got hugely excited by this because for the first time, it doesn't look like a clunky graphical avatar that's got stitched together sort of isolated sign. It actually looks like a real person moving, and it's also, you can understand what they're saying even though the animation isn't perfect. So that was Barbara. Next, this is Michaela. She's a hearing DSGS interpreter, and so we can animate the same avatar from Michaela. And I can even take some fat old man, which you may recognize, and I'm signing BSL here now, and then I'm animating the GAN as well. And the real scary thing is that actually somehow I make the GAN look about 30 years older, but just by some of the facial expressions that I pull. There's one point, I mean, look, there you go. The avatar magically got 20 years older just because it was being animated from me. So like I say, I mean, this is work in progress, but the deaf community have got very excited by this because obviously it's the first time, it's not perfect, but like I say, it's starting to look like a real person rather than an avatar. I mean, we haven't solved all the translation problems at the moment, but actually I think there's huge market for this already in terms of puppeteering. And one of the biggest advantages, I think, is anonymity. Now, in the hearing world, we take it for granted that we have anonymity. If you go on social media and you want to put a message up in text, you can make up whatever name you want and you can write a message. If you're deaf and you want to leave a message somewhere in your native language, then by definition, it is a video of you, right? And so there is no anonymity in that. And so actually the idea of being able to reskin from your video to somebody else, I think it's got huge, huge applications just in terms of anonymity for social media and things like that. But also customization of appearance. Imagine, you know, you could give the home user the ability to choose what their avatar looks like. And, you know, we're also sensitive at the moment about, it doesn't matter what my ethnic origin is. You know, I could choose to have my interpreter be somebody that I want, you know, to look like me or to look like somebody, well, whoever I want. You're just giving choice to the consumer. Like I say, I mean, it's work in progress. This is the most recent results we've got. So this is Clive Mason, who's a very famous BSL interpreter in the UK, which we showed it to. He got very excited. We asked him whether we wanted to do some intelligibility tests. So he's hopefully working with us in order to do that. We want to know exactly how much information is being lost when we reanimate. And actually, I don't think it's that much. I mean, there are artifacts there, but this is it. But we've still not done these intelligibility tests yet. So that's the next thing. Okay, so summary, future work. I'm not sure whether I'm massively ahead of time. I think I am. I'm not too bad, 40 minutes in. So the current limitations we've got are all to do with data. All right, so that Phoenix data set, which was created originally by Oscar Koller and the team over at Aachen University, was hugely instrumental in us getting to where we are in terms of translation, because it was one of the first translation data sets where we had the video and spoken language translations. But and when we started working on that, the error rates were ludicrous, you know, and it really has moved the field forward. But it's such a narrow domain of discourse, and I think everybody's overfitting to that data. So, you know, it's time to move on to something else. But the real problem is that there's real limited availability. I've got linguistic data sets, and I work with linguists all over Europe, and their data sets are so broad, and the domains of discourse are so broad. You know, it might have phenomenally good labeled data, but it's nowhere near the quantities that we would need to tackle the domains of discourse that wide. So what we need is somewhere in the middle. Now, what we tried to do last year was we tried to find some middle ground. And so there's this C4A data set, which is about 190 hours of broadcast footage, and it's all news. And we did it to try and capitalize on basically COVID, because the news was so dominated by COVID in multiple countries that this allowed us to basically build a parallel corpus where we knew that the topic was going to be very similar. We've managed to manually align about 20 hours of that. But again, the domain of discourse in there, the number of singletons in it, make that an extremely challenging data set. So we're going to continue trying to align some of this broadcast footage and across multiple languages as well. So we've got parallel corpora, but it's a non-trivial exercise. So at the moment, our biggest limitation in small domains is data, small domains of discourse. We're working hard to remove the bottlenecks. The first one was, how do we remove our reliance on gloss, which we've already done. At the moment, I need a backbone that doesn't overfit to data. So we're trying to get representations that will generalize across data sets. The ultimate aim is to have a translation system for conversational sign in the near future. And personally, my goal is, to solve this problem before I retire. But I think the singularity is due to come in 2045. And I keep saying to people, they sort of say, when are you going to solve sign language recognition? I said, well, if the singularity is going to kill us all in 2045, one assumes I'll have solved sign language recognition before that happens. So, maybe I'll have to postpone retirement just by a few years. And like I say, one of the biggest problems we've got is data, but also permission to use that data. And that's actually becoming increasingly important, especially with the GAN, because the GAN looks like people. Then that really brings home the sensitivity, because a lot of the data that's recorded by the linguists was recorded for linguistic study. And the people that gave the gave that data didn't necessarily give the rights for it to be used for these things that we want to use it for now in terms of machine learning. And you've also got the problem that in terms of translation, there's two components there. It's the appearance of the person, but there's also the IP in terms of the translation. Who owns, there is more than one way to translate something. I can take the same sentence or paragraph in written English, and I could ask 10 interpreters to translate it into sign, and every single one would be different. And so there is IP in that interpretation. And that also brings up another problem, which is normally we have single language pairs. We have a spoken language sentence and a single video. So we're not actually capturing this natural variability that occurs in translation. And it's much easier with spoken language because the written form of the language, is directly, the written form is the same as the spoken form, where it's not true in sign. Anyway, just to wind up, so the current team working on sign, I've got Jihan, who's a research fellow and did his PhD with me, and he really pushed forward on all the NNT stuff. Tao was working with us on part of Extol, but he's had to return home due to visas now. Ben's in the third year of his PhD. He's been working on the sign production side and the progressive transformers. And then I've got Joe, Ryan, and Harry. Unfortunately, Harry only started a week ago, so I haven't got a photo of him yet. But they started their PhDs recently. This is really exciting for me because actually sign language has always been quite a small activity in the group. So we've never had this many people all working on sign simultaneously. And just finally, one big shout out for Oscar Collar, who did his PhD at Aachen. I've mentioned him a couple of times. I co-supervised him for his PhD, now works for Microsoft. But Oscar did huge amounts for the field and pushing it forward. So I have to give him a big shout out. He's out there somewhere. And I think that's it. Hopefully that's not too bad. I think time-wise, 45 minutes.
Thank you for the wonderful talk, Richard. I think at the end, you brought out some interesting aspects of ethical considerations, which I feel are quite important in this field because we are doing generation. So definitely diversity and inclusion, and of course, the aspect of fake videos and IP. So I think I'll just start off with one question, which I'm really curious about, actually. So we have, you mentioned that, of course, sign language is definitely a visual modality, but it's not just hands, it's faces. And a pre-question before. So is some level of tone of the voice, how you're speaking as a non-deaf person, is that also represented by the facial expressions as well? In some sense, or is that something that's non-existent in sign language?
No. Well, so it's not just the face; it's also the body as well. I mean, so if you were angry, right, then that would come across on the face, but it would probably also come across in the way that you sign, because you'd be signing more aggressively and quicker. So, I mean, take all of the non-verbal communication from spoken language, and then mix that up with a load of grammatical rules, which are really quite complex. And this complex use of space and direction. And this is it, we are nowhere near tackling the full complexity and the color of the language. We've only just really moved to continuous translation from recognizing isolated signs. But I think this is it. I mean, the data's not there. We're kind of where speech was 20 years ago. But we all know that things are moving so quickly at the moment.
So I think that's so a follow-up question to that, actually. Like, I know the data is not there, it'll take time, but I think as a philosophical question, if you were to do translation from spoken language to sign language, and would it, in my opinion, make a lot of sense to, of course, include audio, because that has a lot of nonverbal information, and also just the general body posture, gesturing in general, that would also add to some level of sign language, which is sort of maybe missing right now, because I think right now you're just having text as the input. Does that make sense? Or
no, it does. Yeah. So within Easier, which is the EU project, there's a whole bit of work that's looking kind of at effects and actually, so not just written text, but actually, you know, if it's an audio signal, what other cues are there that need to be transferred across as part of the communication? I think, yeah, putting all of these things together, I think, is the real problem. So yes, I mean, you're right. All of these things exist and they're all issues and there's much more information in there. But I mean, at the moment, I had a meeting yesterday, we're talking about, I've been talking about trying to pool linguistic resources so that we can start to actually tackle some of the things like direction and placement, because up until now, completely ignored. You know, it's such a. There was a really good talk from Gallaudet a couple of weeks ago, and it was one of the talks was from Christian Vogler, and Christian had he had 3 avatars. It was the hand talk avatar, and there were 3 examples of where it was failing, and one was to do with basically homonyms, and it had just got confused in translation and was, using the wrong words. One was to do with lack of non-manuals, which had completely destroyed the kind of the sentiment of the sentence. Things like sarcasm. You think of the subtleties in spoken language, how, if you just wrote it down, it would get completely lost. Well, how many times do we get in trouble over email? And what was the other one? The other one was to do with placement, and it just getting everything kind of jumbled up. So yeah, I mean, there's still huge amounts of work that need to be done.
Yeah, thank you. I think Hannes has a question. Yeah, Hannes.
Yeah, I was just thinking about, it was a really nice talk and I enjoyed it quite a bit. And then kind of like you're already talking about, there's a particular part of the picture that you can focus on right now and others become very difficult. And I'm thinking about group conversations in particular. If there are things that happen in a social context that, most of the examples that you gave is sort of a one-on-one or, a monologue situation. Even in a dialogue, the one person speaking is kind of speaking in front of a camera that is then transmitted and then that is received on the other end. But what happens when you bring in several speakers together into one room and they're kind of having a conversation? And is that something that you could even imagine supporting, bringing a signing avatar into a group chat?
Well, I mean, I think it's like, as with any language, I think as you start to learn, this is why I say, people who want to work in this area, you must go and learn how to sign. I mean, it's just ludicrous not to. But all of these things, I mean, because when you take, in a group setting, a deaf group will move apart. So whereas we will all, a hearing will all stand together so you can hear each other. If you all stand too close together, you can't see each other signing. Right, so a deaf group in a pub will actually all move apart, so you've got a much better view of other people's hands. But also, you try not to self-occlude. You're very conscious of the fact that when you're signing, sometimes you need to drop to finger spelling and things like that. And you're trying to make it easy. So you're very conscious of who's watching you. And so you're changing how you present yourself to make sure that you're not self-occluding the information that you're trying to communicate to them. And that becomes challenging when you're in a group. The other thing that's interesting in the pub, which you don't see in data, is, of course, all the rules go out the window. If you've got a bottle of beer in one hand, right, then you completely bastardize the sign. But it's still communication. It's the same as eating with a mouthful of food. I mean, you do it kind of without thinking. And, if I'm going to point, then, I might do it with a bottle. Or, I might stick it under my arm. And so this, it completely changes how you sign. But humans are such phenomenal things that, we take all of this for granted. It doesn't seem to affect how we consume and understand it. So,
because I was thinking about like the training application you showed earlier, that like at the very beginning, I mean, you're kind of teaching someone to make the signs and they are carefully making them in front of the camera, trying to match the video or the stream that is coming in. You're not preparing them yet for a social situation. You're very much just giving them some kind of almost like an alphabet type of learning.
Yeah.
And I wonder if like if bringing them into like a VR simulation is the only way to really get them the full experience, or as close to it as we can, with several signing avatars or agents around them that they can practice with.
Well, I think some of the tech that is coming out of big companies like Facebook, I think, is potentially going to fundamentally change the way we acquire some data in the future, because I think it's going to open up whole new ways to study. I mean, this is what I said before. I think it's hugely exciting. I mean, the stuff that Yasser showed, you can imagine putting that together, but we haven't solved some of the fundamental problems, and it makes me feel quite embarrassed that we're still faffing around with the weather. We can't even tackle like a conversation. It's just, and it is all down to the data. It's down to the fact that we don't. I mean, we've always had to rely on linguistic knowledge or inductive priors, call it whatever you want, but basically injecting knowledge into the system to overcome the fact that we don't have the data to do it in a purely statistical way. And I don't think that's going to change. End to end doesn't work at the moment because that CNN backbone just overfits. And so at the moment, what we're really doing is we're still kind of breaking the problem down into its constituent components to overcome the fact that there is no such thing as a data set that's going to serve everything. If I can use this data to get invariance to this, and then I can use this data to try and tackle that, and then I'm talking about, can we pool some of the linguistic resources to start to try and look at some of these more complex grammatical structures that at the moment that we haven't even tackled, because I haven't got a hope in hell of doing that just from recorded data. But I mean, if we can solve some of the alignment issues and scale this up to some of the broadcast data, then this is, I'm hoping that soon we'll be able to increase the amount of data that we can use by, at least 2 orders of magnitude. I probably didn't answer the question and went off on one, but
but thank you. No, it was good.
Awesome. Thank you so much, Richard.
My pleasure.
And now we'll head on to the second session of Spotlight Talks, where I think Don will take over. Don, if you want to.
Great. Yes. So in this session, we have 4 papers that are accepted for our workshop. And without further ado, we will start with the first paper on sign language animation through 3D pose lifting by Shyam Krishna. So if you could share your screen and we'll proceed with the talk.
Hi, yeah, just a second. Is it visible?
Yes, we can see it.
Let me just, yeah. Hi everyone, I'm Shyam Krishna, and I'll be presenting sign language animation through 3D pose lifting. We present in our work a 3D pose detection model designed specifically to work with sign language. Its function is to convert pose from a 2D monocular video frame of sign performance to 3D pose parameters, which can be used to control a 3D animation model. We extend on our previous work, which involved rule-based English to Indian Sign Language translation system. In this work, we had commissioned manual animation of around 1,300 signs of Indian Sign Language, ISL. But what we found was that this process is very tedious, and we were looking to automate this process for the remaining signs that are existing. A public video lexicon of the signs of ISL is available, and we were looking to use this to generate the remaining signs automatically. Our survey of existing monocular 3D pose estimation models proved unsatisfactory for our use case. These models are trained for general human motion, and they involve varied camera angles, whole body motion, and not much importance is given to the hand pose itself. Whereas in sign videos, there's a fixed camera in front before the performer, and only the upper body is visible, as well as hand shapes are of prime importance for sign language. One common existing technique of 3D pose estimation is termed lifting, where 2D pose parameters are lifted, so to speak, to 3 dimensions. We found that our data set and 3D model were realistic enough that robust 2D pose estimation performed very accurately on it. So you can see here a sample frame from our data set with the open pose results overlaid on it, and so it performs pretty accurately. And so to further augment the quantity of data that we had, we generated new pseudo signs, which consisted of permutations of hand shapes from one sign with the body motion of another, effectively doubling the size of our data set. And this also works as it limits the motion and the hand shapes to those that are allowed within ISL. So finally, we generated a data set of around 100,000 frames, which we used for training. This is an overview of the architecture that we used. We build on existing 2D to 3D lifting, pose lifting architectures that are employed in research. So the 2D poses is first normalized in our case because we needed to work with different signers that are present in the video lexicon, so they have different body types. This is then further fed into a residual block, which performs the lifting. We also use 2 separate models for the hand and the body, as these two are at very different scales and are equally important to the output. We also found that so current research typically ends up using 2 residual blocks, but in that case, what ended up happening was for our data, it did perform pretty poorly. So we simplified the model to just use 1 residual block. So these are some of the qualitative results. So this is comparing the output of our existing, existing models versus our output for 2 frames from the video lexicon. So we can see here that, in some cases, the hand pose ends up being very inaccurate. But more importantly, what ends up happening is that the lower body is, as we can see, is very inaccurate. So what ends up happening is, so the camera angle and the lower body, when it ends up being inconsistent, when it's used in an animation, the entire body ends up having a lot of jitter. So looking at quantitative results, we have separate results for the hand and the body. So the metrics we use are the mean per joint error, in which case, the lower values are better, and percentage correct key points at a specific distance in 150 millimeters in this case. And for this metric, higher values are preferred. We can see that for the body model, our model consistently outperforms existing models. And this is partly also because of the difference in lower body joints that end up compounding the error in existing model versus ours. When we look at hand models, we see that our technique works competitively. Yeah, so for our future work, we look to implement facial expression transfer as well, which is very important for sign language, comprehension, as well as grammar. And we also look to incorporate temporal consistency. So our model currently works on a frame-to-frame basis, which ends up putting in a bit of jitter in the output when it's used for video generation. And we look to incorporate temporal consistency to sort of smooth that out. Yeah, finally, we'd like to thank the Emphasis Foundation and Minro. Their grants help fund this research. So yeah, thanks. Any questions?
Thank you for your presentation. So I had a couple of questions. Could you maybe go back to the slide where you mentioned about the data augmentation?
Yes.
Yes. So could you explain how like what kind of permutations were specifically applied here with different body like, so I'm assuming that you sampled different body poses and applied different permutations of hand. Could you elaborate that a little more?
Yes. So so hand poses and body poses, so they form something that is similar to phonemes in spoken languages. So they're sort of limited to a set. So what we did was to have a greater variety of poses. Since we had only 1,300 signs, we wanted to, so we take the hand shapes as they appear in one sign, and the rest of the body motion as it appears in a different sign, and combine them basically, and also have some checks and balances so that there's no collision going on and things like that. Yeah.
Right. So then, is it fair for me to understand that you took all the key points until the wrist joint, and then I guess
yes
sampled a different hand and
that's right.
So I am not well versed in this field, so my question that I have is, does this not alter, I guess, the meaning that's embedded in that hand?
So yeah, so for this model, the meaning of the signs or like that part isn't important, because all it's looking at is accurately being able to convert a 2D pose of a certain. So we have these hand shapes which will occur in different with different body motions in the remaining signs, and since we don't see them in our data set, this was a way to augment.
Right, that's really smart. So another follow-up question that I had was, with this augmentation, like is there an ablation that we can see that shows that the augmented data set actually performs better than the one without augmentation? Were you able to see any differences?
Yes, I don't have the result. So what ends up happening is the data set is very small otherwise. And the training sort of it doesn't perform that well. Like it ends up having some kind of a mode collapse or something like that ended up happening. So yeah.
Great. Okay, that makes a lot of sense. Another question I had was, so we know that with most 2D skeletal key points that we extract, the finger is often being very noisy. And if you go to the table that shows the differences in the fingers, like the table, the one after, I think.
Yeah.
So there you basically have a hand model comparison. So I have a question, like, how noisy was the input 2D skeletal key point just with respect to the fingers that you could see? And I'm assuming that you implemented the same data with Simple X as well as Signpost, and you get comparable performance. I'm just wondering how noisy was this the finger key points, and then and what was the effect as a result of the noisiness when you're rendering it to the 3D or pose lifting to 3D space?
So yes, it ends up being a bit noisy. Like it does perform pretty accurately. Like a few years back, I wouldn't have expected such good accuracy in hand, the finger estimation. But even so, like it performs pretty well in converting these into 3D parameters, because I think this is because there's a limited number of hand shapes, a limited number of 3D outputs that can come, right? Like because and so even though there's a bit of noise in the two-dimensional pose parameters, what ends up happening is the model would have learned to sort of go to these to the common 3D parameters. I think that's why it sort of was. That's our guess.
I see. I understand. As a final question, I just want to see understand, I guess. So what are the next steps that you plan on taking with the work that you have?
So we are currently working on the temporal consistency part. So what ends up happening is there's a lot of jitter. So there's a lot of there's a lot of shakiness, you can say in the output, because the open power output and the model itself is temporarily, it doesn't take in any temporal information. Right. So we are currently looking to since we have animations themselves, which are videos, we can learn the temporal consistency from the data as well. So that's what we're looking at currently. And we're also looking at controlling the facial animations, because they're extremely important to sign language, like very important to the to comprehension of sign language as well. Yeah.
Right, that makes a lot of sense. Like including some sort of auto regression taken to the previous context must be like a really important part in generating, I guess, because that would provide us input to the model. Because if you have the prior information.
Yes, exactly. So it also, it ends up, because of the noisiness of, say, the 2D input as well, that ends up, it ends up alleviating that as well.
Right.
Yeah.
Awesome. Yeah, thank you so much for your presentation. Thank you.
Thank you.
Sounds great. So we will move on to our next spotlight talk by Xiaopeng Liu on localized group and select, boosting text VQA by syntax modeling.
Okay, can you guys hear me?
Yes.
Oh, cool. Let me share my screen. Okay. Hi everyone. My name is Xiaopeng, and today I'm going to present our new paper, localized group and select boosting text VQA by syntax modeling. This is joint work with Zhen Fan, Yansen Wang, Dr. Jing O, and Dr. Caroline. So the outline of this presentation is as following. I'm going to first talk about the motivation, the task, the model architecture, the results, and the discussion. So what is motivation for our work? I assume everyone here is very familiar with VQA task. For example, given an image, we want to ask people, for example, how many birds are there in the image? This is a valid question in the previously defined VQA dataset, because it can be it can be mapped to the count question type. But in some other scenarios, for example, if an image includes some text, then the previous VQA dataset cannot accomplish this task, because the dataset itself does not include this. So in conclusion, classic VQA models fail in reading the image. So the task right now is text VQA. This is another dataset, which is special VQA task where text in the image are relevant to the question. So this is much harder and requires model to first extract the text from images and then reason based on the common sense knowledge to answer the question. So our baseline model is the M-forcing model, which the original author just put everything into a multimodal transformer model and then use decoder layers to decode the question. So for example here, what is the speed limit of this road? The first step is to use an OCR engine to extract all the text here, and then use a fast RCN model to extract all the objects and the region where there exists text, and then put all those information into a multimodal transformer model, and then output the answer. But there are actually some problems in this model. The first problem is it's very hard to ground the question to the correct regions. For example, in some cases, the model does not understand which region in this image should it pay attention to answer the question. And the second problem is the input OCR tokens do not have the order information. Because of the limitation of the OCR engine, the OCR token does not have the order information by itself. The final problem is the input OCR tokens are of very poor quality and is not very reliable. So based on these three findings, we propose some improvements. The first is question visual pre-training. So before you're putting all the information into a multimodal transformer and do the decoding part, we design another task as a visual grounding task here, which given an image and a question, for example, what does this store sell? We let the model choose the best bounding box out of n bounding boxes in this in the visual genome data set. And the second part we want to improve is the syntax modeling. So we want to address the problem that the output OCR tokens does not have the order information. So our proposed solution is syntax clustering, which we use unsupervised clustering algorithm like dbScan to try to do the clustering before we put all the information into the multimodal transformer. And the image in the left-hand side is the OCR detection, and on the right-hand side is the after the results after the clustering. We can see that the related texts are clustered together, and this would make the transformer model easier to learn. And the third is the OCR source selection. Because poor quality of all the OCR systems right now, we try to modify the training and prediction process and input and utilizing different OCR systems. And in the inference stage, we just select the OCR engine which has a higher confidence score. So here is the results. It appears that by including all those improvements, and our model can outperform previous models in both text VQA and syntax VQA data set. Here are some qualitative results. So, for example, what are the coloring with this instructional book? And in our model, if we do not use the syntax clustering, then the results would be the coloring. But if we use the clustering algorithm, then it can output the correct results. And the right-hand side example shows what is the number of the jersey on the left. So if we just use one OCR system, which is Azure, then the result is 17. But after we use two systems, then we can get 3 as another output from the OCR system. And this helps the model predict the correct answer. So the last slide shows some field cases. For example, on the left-hand side, although we have all the information from the OCR system, and we can get all the tokens correctly, but we still fail to get the answer because it requires very detailed machine reading comprehension skills, which is lacking in our current design. So this might be one of the future work. And on the right-hand side, for example, how big is the TV? And our model outputs 8K, but actually the ground truth is not 8K, but 98 inch. So this requires very extensive understanding for the whole context of this image. And we think it's a very hard to solve problem. Yeah, that's it for my presentation. Are there any questions?
Thank you, Xiaoping, for your presentation. I actually had a couple of questions. If you could go back a couple of slides when you demonstrated, yeah, here. Sorry, the slide with the images. I think it was 2 above, like this way. Oh yeah, this is impossible. Oh, sorry. So yeah, it's at the result, the one after. Yeah, here. This is perfect. So I'm struggling a little to understand exactly what the role of scene text clustering is with these 2 images that we see. So could you maybe give us an intuition as to exactly what the scene text clustering does, and I guess the hypothesis or the inductive bias that you're trying to embed when you're doing the scene text clustering?
Right. Yeah, sure. So without syntax clustering, for example, in the left image, right, the OCR system just give us 3 tokens without any other information, which is coloring, width, and stain, right? But that is not ideal because we know they are related to each other. So in our system, we give them position embeddings for the same cluster.
Right, that makes a lot of sense. So yeah, I see how basically this is a good example where the light blue indicates the objects that are on the OCR outputs that's on the right of the page and the left, the purple on the left of the page. So I have a question. Just so when you're embedding these positional information of these OCR outputs in the because you have this cluster, could you give us, so like, are you just giving them the cluster IDs? Like, what is the information that represents I guess the clusters, like how is it incorporated in the model?
What we're doing is we just use like sinusoidal positional embedding. So that's what we use to represent the information of the same cluster.
I see. That makes a lot of sense. One question that I had just about this is that, so I know that a lot of VQA models, because the transformer naturally wants some sort of positional embedding, like you add like a position embedding before language, which just gives you the order of the sequence where each word belongs. And then for image VQA, you often include a spatial ordering information where you have like this object is placed here, and you give a relational like embedding that basically tells you this is this far from this object that's on the right. So I was wondering if you have any insights or ablations that demonstrate the difference between these relational positioning ordering that is used in standard VQA models versus your clustering approach, and how those 2 things are different.
I understand the first part of the question, but what like, can you repeat the like latter part of the question?
Right. So in normal, I guess, VQA settings, you basically sometimes use a mask CNN to extract the objects. And then because you also want to feed it into a sequence in a transformer, you represent the order and the relational information of the spatial information by adding some sort of vector that indicates like how far one object is to another. So I was just wondering, in a similar fashion, we can do it on this where, because we have the OCR outputs, right? And then they're located like proximal location in the image. So you can basically represent how far each OCR output is with regards to each other. So I was wondering if you had any insight as to how this method and the assumptions that you make is better than those traditional models that does this approach when they're incorporating order and spatial information.
Yes, yeah, I can answer that question. So actually, previous paper did some analysis on incorporating the like nothing related to the clustering, but just including the position information of all the OCR tokens. Yeah, so they include an embedding called a fork embedding, which is like embedding, including the sizing and the location of all the word tokens, and that actually helps the modeling. The result modeling, it actually helps improve the accuracy. And in our paper, we actually also did the ablation study showing that adding this clustering information helps the model. Yes.
Interesting. That's really cool. That's super clear. Thank you for answering this question. Just one last question. Oh, sorry. I guess let's Shraddha, I think you had a question.
No, sorry, go ahead. I'll ask after you.
No, go ahead. I asked so many questions, so you should go ahead first.
Yeah, so I wanted to say that the same text clustering idea is pretty interesting, and it can be seen with the results that you showed as well. Although I noticed that there can be some counterproductive results with this clustering as well, like the incorrect results that you showed. If you could just go to that slide.
This one?
Right, yeah. So here, if we cluster 8K Ultra HD TV, then that is actually counterproductive because we wanted the individual result there, that is 98-inch. So is there really some way to know if scene text clustering would be useful for a given BQA? Is there some other indicator that we can use and then apply text clustering? Because then we could then combat these kind of cases, right?
Sorry, can you repeat your question, your last sentence?
Yeah, I was asking, is there any other feature that we can use to understand if scene text clustering would be useful or not, say, as part of the question, so that then we can know whether to discount the text clustering and use the individual OCR features that we've got?
Right. Yeah, actually, there are some like disadvantage of our method, and like one thing that can absolutely add, and we haven't add to include is the image feature in this clustering algorithm, because in our clustering algorithm, it's completely unsupervised, and the only input is the location information instead of all the image information. So, for example, in some image, although the like in your human eye can distinguish that like one part of the tokens are very different from another part of the tokens because the color is different, right? But in our clustering algorithm, that cannot be distinguished from one to another, and they are all like clustered all together as one cluster. So that is that is one thing that we did not consider in our algorithm. And but for this case, it's even harder to it's even harder to solve this problem because the OCR engine generates 8K Ultra HD TV 98 for one single sentence. So they they just detect this as one single sentence and they output to us. So there's nothing we can do for this example using our clustering algorithm. And related to your question, like how to distinguish, how to check if the clustering algorithm actually helps or not help. So the score improved, and we found some cases, we find some, previous cases that before using the clustering, it works, and after using it doesn't work, and after using the clustering, it works. I think that can show it's actually an effective approach, but I can't think of any other approach to show the effectiveness of clustering at this point.
Okay, thank you so much, Xiaopeng. And thank you, Shaja, for your question as well. For the sake of time, we will move on to the next spotlight talk. We will introduce Jonathan Windle, and he'll be presenting his work on motion symmetry and conversation.
Hello, can you hear me?
Yep.
Excellent. Can you see the presentation okay?
Yes, we can see it.
Excellent. Okay, thank you. So welcome to this talk on motion symmetry and conversation. My name is Jonathan Windle, and I'm a PhD student from the University of East Anglia. Co-speech gesturing provides semantic context, emotion, and emphasis in speech. So we can see here, can't see my pointer. This addition to conversation serves many purposes, including increased understanding, turn-taking, and listener feedback. Data-driven approaches for automatically driving body animation from speech is an active research area with applications in animation, gaming, and conversational agents. A difficulty with data-driven approaches is often data availability. And so a common approach to combat this is data augmentation. A common augmentation approach in this field is lateral mirroring. So lateral mirroring is to flip the left and the right sides of the body. So you can see on the left is the original, and on the right is the flipped lateral mirror. We raise the question of just how natural is this augmentation? The dataset we used for this analysis is the Talking with Hands dataset, which is a 90 frames per second motion capture dataset consisting of 16.2 million frames of motion during dyadic conversation across 50 participants. There are shallow speakers in this dataset that only performed a conversation with a single other person, and deep speakers that performed dyadic conversation with multiple participants. We began by examining the mean poses of speakers over all of their conversational motion. This aims to reveal any general symmetry of a speaker. Here we see the frontal and side projections of mean poses where the right arm has been mirrored to the left arm. We can see shallow 25 and shallow 6 are relatively symmetrical, the two in the middle, whereas deep 4 and shallow 8 are not that symmetrical, especially when looking at their side projections. This symmetrical difference is further supported by the Euclidean distance of each of these arms when they've been mirrored. With differences in mean pose found, we are interested in the variability of speakers' positioning over all of their motion. When observing the frontal projection of a speaker's motion plotted at 1 second intervals, interesting features that do not symmetrically hold were found. Shallow 25 has a personal trait where their left hand is often touching the right forearm. This is particularly important as the mirror of this trait, the right hand touching the left forearm, is not seen in any of the data. We can also see in shallow 8 on the end that the right hand often raises much higher than the left, whereas in deep 4 and shallow 6, they appear to be mostly symmetrical. We're not only interested in positional symmetry, but also temporal symmetry, particularly if there is a leading hand, i.e. the right hand moves before the left hand. We performed a cross-correlation analysis to reveal any temporal lag between the left and the right hand movements. And we looked at this in each axis direction and the overall movement of that hand. While positionally, deep 4 appeared relatively symmetrical, in the temporal domain, there's clear leading right hand movement by 45 frames. So it suggests that this speaker moves their right hand half a second earlier than the left hand. We also found that this was not consistent across all axes either sometimes. So in shallow 8, it shows that in the x-axis, it is led by the left hand, but in all other axes, it's led by the right. With these findings, we conclude that during lateral mirroring process, characteristics such as self-touching arms could be lost, temporal offsets could be negated, and directional and positional gestures, when paired with directional speech, such as pointing left or right, could lead to a multimodal disparity. A gesture study also found hand usage correlation with gesture types based on handedness, and therefore could lead to unnatural gesturing as well. So, in conclusion, care should be taken when augmenting data using lateral mirroring if the gesturing style and handedness of the original speaker is to be maintained. We also suggest the use of similar analysis to evaluate performance of synthesized motion. This is because the synthesized motion should aim to follow the same temporal and positional characteristics of the ground truth. Including this analysis would provide confidence in the similarity of the speaker's gesturing style and handedness. thank you for listening, and I welcome any questions as well.
Thank you, Jonathan, for your presentation. I think, Hans, you have a question?
Sure. Yeah, thank you very much. It's interesting. I was also thinking about, I mean, maybe I missed it, but did you talk about different categories of gestures and to what extent they would then maybe mirror? And I was thinking maybe some of the examples might include, I'm not sure, do they include self-adjusters? Like if they're actually like scratching a part of the body or something, that then probably they'll only be using one hand for that, or dominant hand.
So this study purely focuses on conversational motion, so dyadic conversation as well, so between two speakers. We mainly focused on, sorry, go on.
So I was just thinking, so do you mean that the data actually already took out all of the non-conversational gestures? Or?
No, so it's purely sort of a 15-minute chat, for example, between two speakers, and it's just all of the motion during that. So there is still self-touching, and as you say, like the scratching would still be in there, for example. But we thought that was kind of important because someone might have kind of like a nervous scratch or something as like quite a personal trait to that speaker. So if that was to be maintained for like the synthesized motion, it seems quite important to keep that on the same side, or like that person, we'll go back to this slide, Chalet 25 often touches their right forearm like this, but never does it the other way. So if you mirror it, it doesn't really hold to the ground truth, for example. Does that answer your question?
Yeah, thank you.
I have a question. So I really like this work because it really analyzed, I guess, almost shed lights on the dangers of augmenting data, specifically when we were doing, I guess, gesture generation, gesture recognition, etc. So my question was, when do you think is a good time to apply this kind of mirrored data augmentation to data? Like for what kind of tasks do you think is useful? And when do you think we should be cautious about it?
Good question. So I think actually, possibly in gesture recognition, it might be fine as long as it's not speaker dependent. It's as soon as there's a speaker dependence that I think there's a real risk with this. So because the gesture, sort of if I point this way, it still holds if it's flipped, but that multimodal disparity may occur if during speech I say I'm pointing left or right, for example. So I think the context of the speech matters quite a lot, as well as if the speaker traits are to be sort of held post synthesis, if you will. But also, I mean, this is some further work that needs to be done, and that is seeing how sort of valid the gestures are when they're flipped, because as I say, like this one and this one would be quite valid, but who knows how valid some of the other gestures are within conversation. There's a lot to it, really.
Right. I think that a really cool analysis would be if you're able to basically classify according to the different types of gestures, such as iconic, dyadic, or whatever it might be, and then see whether for each class of gestures, if it makes sense to do this data augmentation. That would be a really cool idea, because we need more data for gesture generation or any sort of gesture recognition task. It's because the data sets are so sparse and we don't have that much data, and augmentation is obviously a good way to I guess data is everything, like Richard mentioned earlier. So having a good analysis as to when this is allowed, when this is okay, would be a really good thing to study. But yeah, thank you so much for your presentation. This was really insightful. Does anyone else have any questions? Okay, thank you, Jonathan. Then we will move on to the next speaker. Jan Helgason, who will be presenting his work on integrating video with artificial gesture.
Yes, thank you. The video. All right, hi guys.
Hi. Desktop. Sorry, one moment. Okay, I need to restart Zoom to share my screen. I'm sorry. One moment.
Where's Hans, I really like your setup of microphone. It's like very professional.
It's for recording, really.
It does look like that.
Right. Sorry about that.
And optimize for this. Okay.
But now we're just seeing a Zoom screen. Oh, there you go. Wait, now it's Unity.
One moment. There we go.
No. So, do you see the presentation?
Yes, you see it.
Okay. Okay. Sorry about that. So, hey everybody. My name is Johan.
My name is Johan.
And we are undergraduate students studying computer science at Reykjavik University. We'd like to say how grateful we are for this opportunity and how impressed we are by all the presentations we have seen so far. We're going to present to you a project we've been working on for the last 2 summers. This project was made possible by the Icelandic Student Innovation Fund and our awesome professors Anna Sigurður, Steinunn Gróa, and Hannes Högni. So let's get right into it.
All right, so we've all had to experience the shift to remote video communication tools due to COVID-19, this conference being a prime example. These tools have given us the opportunity to communicate remotely and make social connections to our families, friends, and coworkers during the global pandemic. These tools, albeit very convenient and powerful, are not without flaws. In comparison to in-person communication, video conferencing applications fall short in part due to a lack of a shared space and a common frame of reference for nonverbal cues. Our hypothesis is that an application which emulates in-person communication in a shared space while leveraging the off-video communications results in a richer social experience.
Okay, so for related projects, we have BodyChat, which is a text-based communication software developed in 1997 that utilizes shared space and automatic gestures. This was an early attempt to add co-verbal gestures to virtual communication. But a more recent example is Meepo. Meepo is an application which combines video chat with movement in virtual space. There, each user's screen is rendered onto a simple floating avatar.
All right, so what is it that we have built? We designed and implemented an application which combines the best aspect of the video conferencing tools and modern video game technology. Keep in mind, the target platform of the application is conventional hardware used in most conferencing solutions, so no VR headset needed. So in the application, users control an avatar from a first-person perspective in a shared 3D virtual environment. Their webcams track and capture a live feed of their face, which is rendered onto the head of their avatars. The avatar uses an automatic gesture system to produce essential nonverbal cues, for instance, turn-taking cues in the joint virtual environment. All right, so let's show you a demo. Tell me if you can hear the audio.
So welcome everybody to our backyard here in Iceland.
You can hear it?
Yeah, we can hear it.
Great, great, okay. Good thing we're avatars and that we can't feel the cold. Anyway, hopefully my arms are moving right now and you can see them moving. Yeah, okay, great. So this is the automatic gesturing system in action.
Yes, exactly. And the gesturing system is activated by a push to talk button. Show them how it's done, Jon. Yeah, and it raises the arms up like this.
Yeah, exactly. So we're hoping that this can be used as a signal to other users in the environment for a certain user's intention to speak.
Yeah, exactly. And this is super helpful when we're doing turn taking, for example. And we can walk around the environment, and we could, of course, switch the environment for maybe something more for a warmer climate, maybe. And we also have a 3D sound, so we can locate the speakers better.
Yes, exactly. So the spatial audio allows us to, yeah, like you said, locate other speakers in the environment and potentially have multiple simultaneous conversations in the environment.
Yeah, and yeah, that's basically all. So we can get back to the presentation. Thank you.
All right, so hopefully that was entertaining. The main technologies that we used were, of course, Unity as the game engine, and then a bunch of other assets, such as mirror networking to set up the networked application that you just saw. For the computer vision scripts, we used OpenCV, and Agora was our real-time video and audio streaming solution.
Yeah, so here we can see like the gesture state, and so we start in the idle animation, and when the push to talk button is pressed, the avatar goes into a ready to talk pose. Now, when the user starts speaking, we enter this user talking phase, where the avatar transitions between talking gestures through the real-time voice analysis, which takes in the voice stream from the user and hands back a gesture signal. This is a continuous process while the user is talking. Now, when he stops talking, he goes back to the ready-to-talk pose. And if he releases the push-to-talk button, he goes back to the idle animation. So it's kind of like an overview of the gesture model.
All right, so in regards to the current state of the application, there are some kinks to work out and some bugs to fix. But in general, the application is almost ready for user studies, and we hope to be able to form some conclusive studies this spring and report on those as soon as possible. In terms of future work, we plan to add a system for generating non-verbal listening cues, because clear back channels from listeners, like head nodding, for example, are important to the speakers. And currently, those are not being animated by our avatars. We also want to improve the voice analysis system and add intonation tracking for better emphasis detection. This might help us with timing the movement of the hands with the voice.
Yeah, so thank you for listening. And if you have any questions, please let us know.
This was great. I loved it. Chaitanya, do you have a question?
Yeah, I think just generally, I think this is really cool. It sort of felt like a different kind of gather town kind of a thing where you're in the space, which is really nice. Yeah, so I think when you were talking about the avatar itself, you have this push to talk button, right? And I think that is sometimes key to sort of do the turn taking aspect as well. Do you think it's with the given signals, it's possible to actually include that turn taking aspect? So based on what you're speaking, the model sort of figures out that you kind of want to speak something based on your maybe facial motion or just general other signals that you can capture. Is that a possibility? Which, I mean, push to talk makes a lot of sense. It's very easy. But do you think it's a possibility to remove that entirely?
Definitely, we could definitely like skip that step. For us to just, it's like the easier first step to do, and it's kind of also like then you can control like when you want to get the word. But of course, we do these slight movements where we or like open the mouth a bit and tilt our head back when we want to speak. So this is something we can definitely add to the facial or like the computer vision part of the application.
Yeah, I think we initially just wanted to get the most lightweight version of it out, and of course, the more we add in terms of voice and video analysis, it adds to it makes the performance a bit worse. And we were trying to make this accessible to as many platforms as possible. So yeah, I think we want to do it, but we need to look into like how it will affect the performance mostly.
Awesome, thank you. Maybe just a quick follow-up question, actually. Not exactly follow-up. It's a slightly different question, really. So you have these body. So this whole avatar itself, it's rendering out some joint sequences, right? Is that correct? Am I getting that right?
No, it's not. It's actually generating the gestures basically randomly, but they're not built on some predetermined set of animations. So
inverse kinematics.
Yeah, we use inverse kinematics to move the arms around. They are right now essentially random to a certain aspect, but timed to follow the amplitude of the voice essentially. So we get this kind of rhythmic movement of the arms.
Yeah, and that in joint with we also have this hand flick. This is animated, so that's kind of falls up on top of the inverse kinematics. So kind of when we finish the hand movement, we do the flick and we time it. So yeah, we kind of get that the wrist flick in the end.
That's what my question was actually. Inverse kinematics. That's that makes sense.
Right.
Yeah.
Awesome. So I think that's it for me.
Thank you so much for your questions.
I wonder how difficult it would be to integrate like a pre-trained ML model when you're generating these gestures instead of, so for instance, there's like speech gesture, which only uses acoustic signals to generate gestures, and then more follow works does incorporating language, but then the latency during inference with language is like a big bottleneck for you guys. So I was wondering, is that in your future work being able to generate, I guess, relevant gestures instead of, I guess, these programmatic ones that you've included? And if so, like, what are your steps and what are your thoughts on it right now?
Yeah.
I think that would be the ideal,
the
ideal version of the application, where, of course, it uses some sort of trained data, but yeah, we decided to move further from that just to get things up and running as fast as possible. But I think the improvement of the voice analysis system, which we designed it to be a bit decoupled from the gestures, just so we could potentially in the future add any kind of voice analysis or model that would help with making the gestures more accurate, better in all aspects, and really. So
yeah, and like, it's super interesting. I'd really like to try it, like using prosody and pitch, like seeing how the pitch changes in a sentence, and if it like goes up in the end, it's probably a question, at least in like Western languages, and that's also kind of a slippery slope. Like when when we try to make it more direct and more like finely tuned, it kind of overfits the problem, and then when we switch languages, it kind of doesn't work as well. So we kind of try to keep general for now, but we can maybe like find some international ways of how the language is used, and through prosody and stuff.
Yeah, no, this is really cool. I'm just thinking that if you wanted to incorporate this into your system, then you would need some sort of model that's able to predict gestures in real time. And I think that there isn't a lot of work that does like frame level prediction, except for the ones that's done by, I guess, Taras, which is like called gesticulator, but that also uses language. But I think there's an earlier version that only uses speech as well. And I think that's relatively lightweight. So maybe you can try using just the acoustic features to predict, I guess, frame level, I guess, beat gestures or something like that. That might be relevant.
Yeah, yeah, exactly.
Yeah, that's really cool. I really like it. Richard, Tanya, am I getting this right? I think there are some works like that.
I mean, I think you got that right. I think there's some more work on, I think by Taras also on real-time stuff. So it might be just better to look at his website. So they also try to have a real-time animator, an avatar of sorts. So yeah.
Cool.
Yeah, nice.
We'll definitely look into that.
Yeah. Thank you.
Thank you so much for your presentation.
Right.
Thank you.
Thanks. Stop.
Awesome. So now we are at the end of the spotlight session. So back to session 2, I believe, for the keynote speakers. So I think Maya, I saw Maya come in. I'm just, Maya, if you want to start sharing your screen, we are kind of ready for the next talk.
All righty.
So just a quick introduction. Maya is Chan Shun Xiong Distinguished Professor in 3 departments, Computer Science and Neuroscience Program and the Department of Pediatrics in the University of Southern California. Her interaction labs research focuses on socially assistive robots. And what I really love about her research is the intent to first perceive and understand human behavior, and then build technologies that can like really endow robots with the ability to help people help themselves. So there are so many use cases in real life, and especially in rehabilitation for brain injury survivors, therapies for children on the autistic spectrum, and also education. So it was really cool to see that her work is often deployed in real world settings. And I'm really excited to see what she has for us today. Over to you, Maya.
Thank you. Well, I decided that I was going to put a whole bunch of recent work for my students. And so there's going to be a bunch of new stuff, which I'm excited about. And I'm going to say up front, I'll talk about a bunch of things. I hope there'll be time for questions, but if we don't cover all of the questions, always feel free to email me, and then I'll answer or I'll send you to the person who can answer that cogently. But I'm going to cover a lot of ground because that way I figure lots of people will find something interesting. But thank you for the intro. It does exactly characterize what we do. So we do this sort of very broadly construed socially assistive robotics, the idea of people helping themselves. But really, it's this combination of understanding the user ideally in real time, having models of key aspects of relevant behavior in order to predict and support, tapping into our social, what drives us as social, social creatures fundamentally. There are a lot of applications, as you said, and we're always grounded in real world domains because I really don't believe in not real world data, as you will see repeatedly. And so we've done this for 17 years. We've gone out and worked in a variety of domains and have discerned in many ways what is fundamental across people and then what is individually specific. And that's really important today because machine learning is booming, but there are also some assumptions about machine learning and ideas of big data that may not apply to a lot of behavioral interventions and therapies where individual adaptation is so much more important and personalization is so fundamental and then so very, very difficult because of individual variance. So I'll get to that. but it certainly keeps our lives interesting. We're never bored. So at a high level, what we want is we want to generate and sustain motivation and grit and adherence to healthy, desirable behavior in people through technology support. How do we do that? Well, we usually pick some behavioral phenomenon or phenomena, and you'll see me talk about. So we might talk about personality, we might talk about engagement, we might talk about deception. I mean, you'll see an array of phenomena that are relevant to interaction. And then we model those phenomena, we model the user, and then ideally we personalize to the user. Not every piece of work does all three, but that's sort of our arc. Now, of course, we do this with physical robots, not necessarily like the one that you see at the top that's large, but nonetheless, we do it with physical machines because we want to be in the here and now in the physical world with the user. And that brings in a huge amount of complexity, of course, the body does. So let's talk about some kinds of things that we've looked at that have to do with the machine being embodied and the user being embodied and them having to interact in the physical world and understand one another. So some early work of Ross Mead was all about proxemics and just even understanding where the robot should stand and move relative to the user. And I don't want to go into this because this is past work, but I just want to establish that even the very fundamental things like where do you stand have a real impact on the interaction because everyone impact, well, in a dual interaction, in a dyad, you impact one another. In a group, it's even more complex. Here's some fun movement demonstration just of what it should look like. When it works well, it's like dancing. When physical space doesn't work well, it's bullying.
Stop it. You look like you are about to kick me. Please don't kick people. It will physically hurt them. Stop it. Pointing and laughing at people is not appropriate. You should not do this because it is demeaning.
So why did we do this? So we were interested in understanding bullying, helping kids understand bullying, whether in themselves or in others, and then respond to bullying appropriately. And it was a very interesting project because you might start by asking, how do you get bullying data? And you can get actors to act things out, but those data tend to not be genuine, as a lot of work has shown, and don't necessarily generalize. And so there's this really interesting process that my former student Michael Tsang did, in which he created a sensitive robot that I just played the video for you. And then we showed it to, I don't know, about 1,500 children in an open house. And what do you think kids do when they're around a sensitive robot that tells them not to bully them? Well, of course, they bully it immediately. And so we collected a bunch of bullying data or mock bullying data. And then we used it to train models, et cetera. But to me, the most interesting thing here is how do you get at complex behaviors and data for those complex behaviors. So we'll talk more about that. Now, as you can imagine, the robots that we use are not always expressive enough. And so one of the things that we're getting into is this new growing field at the intersection of robotics and mixed reality. And it's the idea that if you have a physical system, you can overlay a shared world in this mixed reality. I prefer AR to VR anytime. I like being in this world. And so we're using AR, lightweight AR, sometimes just through the phone, to help users see the robot as more physically expressive in order to understand the robot more and also to share a richer world. So for example, we're using this to teach kids STEM content like coding and math, but also as you see later in the talk, when we go to the learning section, we also are teaching them how to interact better through physical movement because movement and thinking are so deeply connected in embodied animals. But there's this really interesting, rich area of mixed reality and embodiment that I'm really interested in seeing grow. And by that, I don't mean embodied things in VR, because the problem with VR is that you're not in the physical world, you're in the VR world, which can be very compelling and great for training. But there are also debates about generalization. AR is very different because you are in this world, but also in the shared world. So there's a lot of opportunity there. I think that's going to grow in some really interesting ways, and I'm happy to see it happening. Now let's talk about how important embodiment can be in some contexts. So one of the projects that we have absolutely requires us to use a physical robot and to use this type of physical robot. So let's talk about a context. The context is we're working with young infants, 3 to 9 month olds, and we're trying to get them to do motor movement training because they're learning delayed for various reasons. It could be autism, it could be injury at birth, various reasons, right? So how do you get a baby to do a movement that you desire? Well, you can move its body parts, but that doesn't, the brain has to move the baby, otherwise the baby isn't learning. So how do you get a baby to do something? Well, it's really hard. You know, they don't know much and you can't tell them what to do. But it turns out they do have these active mirror neurons, like all of us, that basically make us imitate within our minds, but we don't actually express the imitation, except with babies, they can under the right circumstances. So we're tapping into that, right? We're taking a baby and giving next to a baby a robot that is about the baby's size so that it can trigger these mirror neurons. And then it's creating motions to trigger the baby's behavior. And I'll tell you what we model in all of that. So, but you have to see the babies move because there's just nothing better than that. So the robot demonstrates motions for the baby and eventually the baby learns. Babies are pretty smart. They learn in about 2 minutes. So you may think robots can learn faster, but really not anything particularly complex compared to babies. Now, the interesting thing is the baby is actually learning contingently. If you take the robot away, the baby gets upset and they start responding to the robot's movement and they get happy, which is good. Now, here's the interesting thing. We can actually model what stimuli visually will be surprising to the baby. And that means we can drive the baby's attention because, you know, with babies, when they see something that's visually salient, they will look at it if it's surprising. And then when they look at it, they're likely to move in a particular way in response to it. So you can basically drive the baby's behavior by predicting where they will look by modeling their surprise. And so we use the model of Laurent Ety and Pierre Baldi that was trained on adults and tested it on baby data, and it worked because, you know, the visual system is the same visual system. So that's exciting. And so now we can predict where the baby looks, and therefore we can drive the baby's movement and train them to do the practice, the movement that they need to practice, which is pretty darn exciting. And now for something totally different. This was just hot off the presses. We just did this and wrote a paper on it. And it's the perception of gender in robots, nothing to do with babies. So, you know, people are creating machines and we as humans are extremely biased in our perceptions. So we perceive gender without, you know, being cute. We just can't help it. So now the question is, how do we design robots that have the desired perceptions in users? And what we did is we did the study where we used a humanoid scaled robot. Here it is on the far left in its undressed form. And then we dressed it in what you might construe as traditionally male and traditionally female outfits and put the robot context in traditionally, well, let's see, in 2 different task settings, let's say. And we also used voices by picking a particular voice and then adjusting the pitch to make it more female or more male, which was important because otherwise, if you have different voices, then there's bias. We found some really interesting results, and this is about multimodality. So voice has a strong effect on perceived gender, and we know this because we hear, like even without vision, obviously voice has an incredible impact on how we perceive the gender of the speaker. But if the voice is androgynous, then clothing shifts the bias. And unfortunately, the bias is very strong. So for example, if we said that the robot was a service worker, a receptionist, people saw it as more feminine. And if the robot was a medical professional, they saw it as more masculine. So this is very interesting, right? Because what we're seeing is people are putting their biases, and this is a Mechanical Turk study. So people are putting their biases on their perceptions, and you really have to manipulate the appearance of the robot in order to really have to push it in a relatively extreme way in order to combat some of those perceptions. And of course, they're cultural. And of course, this is really complicated and deserves more work. And I know people are getting into this now. We were just interested in doing it because we got this new humanoid-sized robot, and it was a fun thing to try, fun and a lot of work. But it is an area that is going to be fraught if not treated properly because of all the bias that we as humans bring to these interactions. So another fun area to open up and get people to start working on it. All right, so that was a bit about embodiment in different contexts. Now let's talk about interactions. You know, everything about human interaction is complex. Things like turn taking, which are so fundamental and so basic, are still difficult for some individuals and are still difficult for robots. And so you'll hear, I'll even mention turn taking again. We've been working on it forever, so have other people, but it's still very, very complex. It's a very subtle social dynamic. So we'll talk about various things. One thing that we modeled a while ago, and may return to at some point is personality. The idea that how we move, how much we move, how close we get to someone, and how densely we speak, words per unit time, is a way of conveying personality very powerfully, especially on the extroversion introversion spectrum, without even paying attention to what it is being said. And then matching that personality of the agent to the user has very powerful effects on their time on task and their enjoyment. And so we did this work a while ago and found very strong effects, and are now looking at doing it with added things like emotion in voice and actual content of speech. Now, some more recent work that's really interesting from Lena Mather in my lab, an undergrad who's applying to grad schools, by the way, who did some really nice work on court trial testimony data, which was labeled for deception and non-deception. And she did a multimodal model training the data in order to show that she could improve the detection of deception by using multimodality. And so it was very interesting to find out which cues were most important. Even more, now, of course, not of course, but she demonstrated through quite a bit of work that multimodal models outperformed unimodal ones. But what I found even more interesting was the subsequent work where she was able to train learning models with unsupervised data. So generally in deception, right, you're not always, or very rarely do you have the luxury of having a labeled data set on who did and didn't lie. Now in those court testimonies, one does have that data, but typically it's rare. And so it was very interesting, actually she got a very high level of accuracy for looking at unsupervised learning of deception. Now, I think this tells us something interesting about deception. It tells us that deception, first of all, we know that humans are terrible at detecting deception. We're at chance. We're at 50-50. Yet machines are very good, and even with unsupervised data. So what is that unsupervised training? What does that tell us? Well, it tells us something about deception being a pretty stable, common thing that goes across users, which is a rarity because that doesn't turn out to be the case for some of the other behaviors that we're going to talk about. So, when I start talking to you about autism, we're not going to be able so nicely to work on as easily on unsupervised models. So let's see where we go with that. But it was very interesting work. Another phenomenon that I just find endlessly interesting and incredibly important in humanity is empathy. So the idea that the user can empathize with the robot. And conversely, and this is the part that we're more interested in now, the robot can elicit that empathy. So the robot can demonstrate empathy, right? And you can argue that the robot is not really feeling empathy, but empathy is not about what you feel, it's about what you do. It's the action in the world that is socially perceived, right? The empathy is powerful because of the person who is receiving it, not because of what you internally may feel. And so that means that we can create robots that demonstrate empathy, but perhaps more importantly, we can create robots that elicit empathy in people, get people to behave empathetically. And so that's what we studied. We studied what kind of storytelling by a robot can make the listener, the human listener, feel more empathetic. When we looked at first, and then we modeled empathy. So interestingly, first of all, we found that first-person storyteller is always found to elicit more empathy than a third person, which kind of makes sense, right? If I tell you, oh, I was hurt, you'll be more empathetic than I tell you, oh, my sister was hurt. And it was also found more trustworthy. Interestingly, we also found that people who reported feeling empathy also expressed it unconsciously in their facial affect. So now we went about taking those data and modeling empathy. And as far as we know, this is the first multimodal empathy model for storytelling. And so, there's some really interesting results on actually being able to model and predict empathy. And this is useful, right? Because we would like to understand more about how we can elicit empathy. It's hard to not listen to the news and see about all the polarization and the idea that empathy is the path to decreasing polarization. So how can we generate it? How can we elicit empathy? So this was really, I thought, quite interesting work just being presented, I think, this week. Some other stuff related to interactions among people and people being good to one another was modeling group interactions. So as you can imagine, one-on-one dynamics are complex, but multi-party dynamics are even more complex. And so we started this work in the lab with Elaine Short, she's finished now and a professor, but she started it by looking at how do you model the resources in a multi-party interaction, and what are the resources? And the resource is the conversational floor, who gets to talk. And also maybe if there's an object being shared around, like something being built or understood, then that too can be a resource. And it's a really interesting way of modeling it, because the question is, what do you optimize? Do you optimize how much everyone talks? Do you optimize how quickly you solve the task? And it turns out, depending on what you optimize in this resource allocation problem, you get very different outcomes in terms of group dynamics. So if you optimize for solving the problem the fastest, the group, of course, can then find a solution that ends the interaction, but their sense of not just empathy for one another, but their sense of cohesion and enjoyment is very low. On the other hand, if you balance for everyone's involvement, in some ways, almost unsurprisingly, cohesion is higher. People talk more. Even the people who are told to talk less later report being happier about the interaction. And interestingly, you bring the people back 2 weeks later and you have them interact without the robot, and the effect is conserved. They're actually, even if you put them in a competitive task, a zero-sum game, they still show more empathy to one another. So this idea of moderation and optimizing the right resource, which is basically sharing, has a very powerful effect in group dynamics. We're scaling that up now and moving it into the context of support groups, where you really have this idea of multiple people needing to talk and really to reveal sensitive information in order to go through recovery. And so we're looking at, how do you elicit trust? How do you share just the right amount of information over time? And of course, this is now getting into the semantics of what people are saying. And of course, the first thing that comes up is turn taking, because if someone is revealing a sensitive piece of information about themselves, the last thing that you want to have happen is someone to interrupt them, because they're not going to talk again. And so this multimodal turn taking is still complex. And one of the things we just did, Chris Birmingham, with others in my lab, was predicting turn taking. And again, using a multimodal approach, looking at face detection and eye gaze in order to significantly improve turn-taking prediction. They just won an ACM multimodal challenge. And again, I think it's really interesting because it seems entirely obvious that you should look at eye gaze and audio, but people don't. So multimodal. All right, let's talk about learning a little bit. So remember, I told you earlier about the mixed reality, using it to enhance the interactions between, in our case, people and robots. And so we're really interested in using this mixed reality environment in order to encourage learning and encourage movement of learners. So it is well known that if you move around, you actually retain information better. That must be why we're sitting all the time when we're learning. But at least young kids don't have to sit. And so this idea of kinesthetic curiosity, that we can stimulate curiosity and movement in a shared world where there could be objects and concepts and creativity. And so that's what we're doing, and scaling up with experiments to see how we can adapt this interaction in a mixed world in order to improve both the amount of movement and the amount of learning, because they are correlated. All right, so I'll just skip that. All right, back to babies. So, I told you about, we were using babies and robots to try to stimulate baby movement. We're also looking at infant and caregiver interactions. This is a really powerful context and very, very challenging. So we know that young infants are in their development are completely dependent on stimuli presented to them, which, by the way, makes this year really weird with faces of most people around infants being covered. But that's a separate issue. So if caregivers are experiencing stress and they're not making eye gaze and they're not turning their faces to infants, then infant development is actually impaired. And then there are long-term effects. And so how do we capture this and how do we model it and how can we understand it over developmental phases? Because infants express themselves very differently at different phases, right? When they're younger, like we're talking 2 months, 3 months, they move, they use their hands, they put things in their mouth. And then as they get older, after 3 months, they can start reaching. And then eventually they start vocalizing in a directed way. So this is a really interesting multimodal, but also time series problem, because developmentally it changes. And so Lauren Klein, with a set of collaborators, is bravely stepping into the breach here, looking actually at complex systems models to understand the dyadic evolving interactions between the caregiver and child, and really looking at individual behaviors as they evolve, and then interactions, the dynamics between the two of them. And it's really interesting because you can look at all kinds of different methods to do this. And they all have their issues, right? So from the older ones like dynamical systems to the newest ones with machine learning, none of them are perfect. They all have issues. And it's really just really interesting, rich area to study. And I want to finish up with our biggest study, which was putting robots in the homes of children with autism for at least a month or more. And it was a huge study. We did it collaboratively with Yale. Yale did the 20 deployments over in their lower income neighborhood, and we did it in inner city LA, and then looked at collecting data, basically helping kids. I'll play this video briefly so you can see the context. This is the context.
Meet Adrian, age 6.
This is some great work.
And his robot friend, Kiwi.
You are doing an amazing job.
On this weekend morning, they've settled in to play some games, along with big brother Darren. Adrian is on the autism spectrum, and Kiwi is no toy. It's a socially assistive robot.
You are doing really great. Keep up the good work.
So the interesting question you can ask here is, well, he's already got a screen, so why does he need the robot? Well, the whole issue is that when someone is learning from a screen, they're not getting the help and support that they need if they get stuck. And also, if they're doing really well, they might not have their level of challenge adjusted properly. Additionally, even if you're thriving in learning the content, the subject material, you're not learning any social skills by learning from a screen. And that is, in fact, what children need in school is the social interaction developmentally. Actually, well, everyone needs it. And so that's something that, of course, we saw in this last pandemic year when kids all had to be learning from home and they were missing the developmental stages of the social development, the eye gaze, the turn taking, being supportive, empathetic behavior, all these things. And so that's what the robot provides. It provides the social as well as cognitive support. But it turns out to be incredibly difficult to do this with kids with autism because of the variance. So first, let's talk about how does the robot adapt to the child. So it's not enough to do just like a ITS and adjust the level of challenge of the content. You also have to adjust the level of support. And so you do challenge, but you also do feedback. So think of some edge cases. If the child is failing completely, if you keep just lowering the challenge and you don't give them any positive feedback, well, nothing happens, right? They don't learn, they get discouraged, they think they can't do whatever, and they walk off. And we do this all the time to kids in school, actually. We say, oh, you're not good at math. And now you think for the rest of your life, you're not good at math. But of course, the trick is to put the challenge at just the right level and to give them enough support and positive feedback, like shaping, to get them to have some success and then have them believe that they can actually do it, right? Same thing the other way. If someone is thriving, if you just give them positive feedback, they lose the challenge, they don't develop grit. It doesn't lead to optimal learning. Optimal learning is actually a certain level of frustration and challenge. So finding that level for each person is very hard because it's both individual and varies over time, depending on the type of material that's being learned, type of skill, type of knowledge. So it's a really interesting set of dynamics, again, to be worked out. But what's particularly hard, both for cognitive and social learning with this population, is the variance. And so there's a PCA figure looking at basically just the changes across participants, within participant and across participants. So within a session, across session, like they're just their engagement and their behavior is related to engagement. You might think that engagement is, well, if I'm looking at the robot, then I'm engaged, but not so, not in any simple way. There might be atypical eye gaze, or it might be that they're looking, maybe they're doing joint attention and bringing the parent in, or maybe they're looking at the robot, but they're just tuned out. So it's quite complex. So it's really, really interesting, complex multimodal problem. Again, multimodality wins out. Applying early fusion of all modalities works much better than individual modalities. Certainly vision is a big indicator, but it is not the ultimate thing, especially in autism where visual patterns are atypical and very individualized. And so it's such fertile ground for doing work. Of course, we applied all of the machine learning models that you would imagine, and we did get high accuracy in the end. But I think there's some really important lessons here, including that more data doesn't mean better learning. And this whole transfer learning problem is so hard here that now our later work, which we're about to publish, really talks about training on each individual user's data, however sparse it may be, but training on early sessions iteratively rather than taking cohort data from other users, because it just doesn't, there's no generalization or very poor generalization because of the variance. And this is not, you don't have the luxury to say, oh, well, that's autism. There's a lot of variance. Everywhere else there isn't, because that's not in fact true, right? We have the same kinds of challenges looking at behavioral phenomena. For example, anxiety, which is very multifactorial and personalized. So how do we deal with these interesting challenges in behavior, in the behavioral contexts? That's a great area of research. And to make progress there, we really need multimodal long-term data for personalization. And so, I just want to emphasize, every user is different and every user changes. And so we really need to look at these social dynamics that are continually shaped. And I'd say there's just not enough work on this. Let me show you something that we did 5 years ago. Beautiful work. This is a little user, 3-year-old with special needs, interacting with a robot in real time. This involves social behavior because there has to be eye gaze and turn taking. There's also physical behavior where she has to actually move a thing on the screen from one place to another. There's cognitive involvement. It has to be the right number. And there's verbal behavior where she has to say the right number. And then the robot, when she says the right number, when she has looked and moved a piece, repeats the number, nods, and then the game advances. So let's look at that in real time. If I can find the cursor, there we go.
From 1 to 6. Count them out loud with me. 1.
Eye gaze.
1.
Physical, verbal, eye gaze.
2. 3. 3.
And it goes on.
4. 4. 5.
I think you know the numbers, but what I don't see is I don't see really almost anyone going out there in the real world. This was in a special needs preschool. So I don't see people going out there in the real world and collecting data. And why don't we have these systems? Why didn't we have this during the pandemic when kids couldn't go to preschool and get this kind of assistance? Because here's a very rich, multimodal, real-time, physical, social, and cognitive interaction. That's the kind of data we need in real world settings so that we can really understand phenomena and then, make a difference in trying to learn, model, and do interventions. And so I think this is a really exciting time. A lot is going on. We know we can do a lot. We can improve health outcomes. We can literally improve life outcomes for people. But we can only do it if we go and work in real world data, real world contexts on real world problems. Don't just download things off the web and think you're doing important things. That's my big pitch. It's a tremendous time to do really exciting work, but it's got to be the hard work. So I hope everyone will be motivated by that, the way that my wonderful students are. I'm very grateful to them. This is the photo on the bottom from 2019. But we are getting together. In fact, later today, we're going to carve some pumpkins. So here is to the return in person as well. And I will stop now and take questions if there is time.
Thank you, Maya. That was a really great talk. I think we have definitely have time for questions. Someone raised, Hannes, if you want to ask a question.
Yeah, hi Maya. This was, of course, always very fascinating. And also, I think you're very brave, really working with robots. I haven't dared to do that yet. I'm still just using virtual humans. It's so much easier. So I was just curious. I mean, there are definitely some mechanical limitations you have to deal with. I mean, I'm thinking about all of the spontaneity that goes into conversations and interactions with humans. And do you feel constrained by the mechanisms? And do you feel like those are changing or getting to the point where we can do things we're not able to do? And I was looking into this maybe 10 years ago, or?
That's a really good question. And I think the answer has two sides. One is that the physical robots are limited. They are constrained. I really wish they were much more capable than they were 10 years ago. I'm not sure that's the case, although I do think we're getting to a point where enough startups and even big tech, like, Amazon just announced an in-home robot that has some level of affordability. So that's good. So we have moved forward. But no, they're not amazingly capable. But what you have with the physical robots that you do not have with screens, and to some, or even AR, VR is a different game, but is that people because we're wired to be social creatures in the physical world, people suspend disbelief and they engage instantly. And so what you get, now I say instantly, of course, those who have issues engaging with other humans might take a little while, but what happens is you get this really, really rich interaction that is much, much more similar to real, human than human screen. And that is just a fact. And so, there's evidence now going back 15, 20 years to show that even the simplest of robots, like what I would call super dumb little boxes with wheels, elicit trust, disclosure, empathy, and lesser, more obvious stuff like turn taking and sharing, etc. So that is the hook. The hook is that we are social creatures, and when we're around physically embodied social creatures, we behave in very natural social ways. And I think that's where you get the really rich and interesting data. And that's also where you have the potential to make, hopefully a big difference in the real world. But yes, you're right. The robots are still not amazing. My point is they don't need to be. I mean, I still wish they were better. Believe me, I wish they were better. But on the other hand, I will also say that one of our major impediments always in robotics has been perception. So, there are two sides, right? There's the perception and then there's behavior. And the embodiments are getting better. Soft robotics, I put a huge, huge expectation on soft robotics, because now we can start making bodies that are, they don't have to be miraculous, but they could just stop being so hard plasticky. And that's going to make a difference, right? But perception has made a huge leap. And when perception makes a huge leap in any technology, then you get so much better interaction and therefore engagement and therefore richer dynamics. So that's really helped us. It's helped everybody.
Yeah, I'm looking forward to getting some robots in the future. I mean, or maybe in the near future.
Do it. You can do it. Join the club.
There's also the expensiveness. I mean, they're a bit expensive. That's another thing, maybe.
Yeah, so that's a really good point. And in fact, I was in some panel like earlier this week, and we were all lamenting how we are still building platforms, right? So when I started in robotics, like my master's thesis was like, I had to build this trash can looking like robot. And here I am, let's not say how long later. And my lab is actually developing in collaboration with Cornell. Cornell has this adorable little squash and stretch robot Blossom. And so we're taking that and we're collaborating with them to make it more capable because it's cheap. There's nothing else that's really cheap out there. You see startups and they have robots that could be cheap, but they're closed box, right? They're not open APIs. Now I have no stake in Amazon, but I think it's interesting that they have a robot that's like, they say it's like $1,000, which is relatively cheap. And if they make it about those skills, right? If they make it a platform eventually, then it might be more accessible to people. Because one of the things that is really difficult for the field is that even if you make your own platform, and my lab has done that, like every 8 years or so, we have to make another one. But those are not commercial products. They're not robust enough. And so that's why we need companies to build them so that if nothing else, they'll really, like, I want to do long-term studies, but for me to leave a robot somewhere for 3 months, 6 months, wow, is it going to last? I don't know, right? That's why it needs to be productized. And that's why I'm optimistic that, I'm hoping that now that Amazon did it, maybe others will jump in and we can start buying robots that are under $1,000. And, it's not perfect. Like the thing that they have, it's got a screen, but it's got enough affordances, I think, to do some interesting work. So I'm choosing to be very optimistic right now, actually.
Great. That's inspiring.
Yeah, I mean, of course, Amazon will take all the data. So, you know, you kind of have to, that's the trade-offs. But if you can also get the data, then yeah, so that's the trick. But I think that's where we're headed. I think there will be enablers because there's a market that, for example, the pandemic, I think, opened people's eyes up to various things that some of us have been saying for 20 years. Hey, you know, people need some support in the home. They need social support. They don't just need things that are physically done for them. They need social support. And I think the notion of social support was so foreign to everybody until the pandemic. And then suddenly people started to realize, oh my gosh, isolation is bad. What do you know? Yeah.
Maya, this was a wonderful talk. Thank you. I'm jumping in. I don't know if I was in the order of question. I think I always knew in your work the multimodal aspect of your work, but in this talk, I think you said the word at least 20 times, which is almost as much as my talk. So but you also emphasize the perception. From your perspective, like when you're really looking at multimodal perception as part of a full system, like that's really part of a full interaction, where are the technical challenges? What are the challenges from your perspective for multimodal? Did we reach a level that you're like, okay, guys, we're good now. It's about interaction or embodiment. From your perspective, where are we in I don't know, your dream or your like, yeah.
Yes. My dreams are always far ahead of me. But that's a really good question because yes, you're absolutely right. The reason why I'm hammering multimodality is because I still see too much work happening on just like, okay, just vision, you know, but maybe vision and audio, but I'm sorry, that's not even all of it, right? I mean, like I want, you know, one body pose, and in fact, I would love to go also with physiologic data. So now these days I'm getting quite wild, but I'm frustrated that you don't have perception for that. Like, yeah, let's not go into $1,300 wearables. So back to your actual question. It is a really good question. We still have to compromise, right? So here's a very obvious example. If I have a robot that is nicely socially embodied, and in fact, you know, it's moving around very naturally, right? Well, it's going to look away and now it's not seeing you, right? So now we've got this whole issue where I want data, I want complete data of the user, but I also want to behave and be embodied in a way that isn't creepy. Because if I have a set of eyes all around my head, that's creepy, right? And so yes, perception is not trivial, but video is getting so much better. Audio is fantastic. And by that, I mean both the physical and also the, you know, all the machine learning stuff that people have been doing. So I'm quite happy. Now, let me give you one example of the practicalities of this. So for example, we're looking at putting some low cost robots in dorms to work with students on anxiety and depression. Okay, so this is a huge ethical issue, right? Oh, you know, you can't put a robot in someone's room because someone else might see it, consent, blah, blah, blah. True, real, right? So I said, well, okay, we could put a camera on it and a light. And anyway, it's never light enough in dorm rooms. So it's like, okay, put a light on it. And when the light is on, that's when it's recording. Because if it records when the light's not on, it can't see anything anyway. And when the light is on, you can see that the robot is recording. Therefore, privacy issue is addressed, right? But that's an example of the kinds of games that we play, right? So like for multimodality, we ended up doing a lot of stuff with audio and video because, you know, the audio wasn't perfect and you can always finesse it. So that's the issue of in the wild. If I'm in like, you know, I have a lab that has a lot of microphones and cameras, but that's not real. That is not what the real world is going to be like. And so that's why we tend to take it out in the wild and then see what we can do with the limited, you know, constrained perception. Because I feel that that's ultimately more real. Because, you know, people are never going to want a ton of cameras in their house. That's just not, or at least not in the near future. There are a lot of privacy issues. And so, you know, people are strange. They're willing to have a camera on the laptop that looks at everything, but then, you know, they don't want a camera mounted separately because now that's somehow weird. And it's okay for the phone to be listening, but, you know, I don't want the robot to have a separate microphone. So there are all these interesting psychological things around perception that we have to overcome. And I think people have this kind of, I think people just want to believe, a lot of technology people want to believe that like, oh yeah, well, 50 years from now, it'll be different. but I'm not convinced. You know, human nature is human nature. And that's been always, you know, you've heard me say this before. I mean, I think people are who we are, and we don't change at a pace that technology changes. We adopt technology, we adapt ourselves a little bit. But especially if you look at older people, you see people kind of reverting to their core drivers, behavioral drivers. And you can't change that. And so I think it's interesting to think again, what does it take to work with limited perception in the real world? And that's where we get into this really interesting stuff like, okay, I'm not always going to understand what the user said. So I need to cue them occasionally to help me. How often can I do that without frustrating the user? And how can I use that? So when I'm going to ask you to repeat that for me, can I use that to engage you, to actually make you feel like, you know, hey, I really care, right? So it's all about, you know, it all like, or being funny, like, oh, you know, I am just not as smart as I look, you know, that kind of thing. Like, so there's humor, there's engagement. That's how to get around these inherent limitations, which I don't believe will perfectly go away ever.
Mm-hmm. No, that's very insightful. I think the aspect of limited, but also privacy and privacy could be also in the AI, could be external because of the light or explicit as a light, or it could be within the algorithm. And the aspect of trusting the AI and allowing the AI to be wrong sometime, but at least aware of its wrong assessments, I think can be, yeah, no, that's all very good. Thanks.
Thanks. Nice to see you.
Yeah, really great.
So I kept my talk short and fast because I always figure the Q&A is the best part. So I hope people will ask questions because to me, this is the best fun. Like, yeah, just reading off of slides. Like, nah. So yeah, so I hope people will ask questions.
I would even maybe follow up with just what we were just discussing, because if you're thinking about the social robot always recording the interaction for analysis and things like that, and being worried about privacy in that context, have you considered having a separate robot that does the documentation and can therefore look at the interaction from the outside, but then you tell the person interacting with the actual robot that they're supposed to interact with that robot does not record anything, that robot can be fully trusted with anything you tell it, anything you do with it. And if you want to have a private conversation with that robot, it's the other robot that they have to turn off, or at least, you know, usher out into the hallway.
That's really interesting. I definitely have not thought about that. The immediate thing that comes to mind is I don't want just the side view. Like the really interesting view is eye to eye. So you could have the second robot like behind looking, but nonetheless, your point about sort of who is the trusted party is really important. And I agree. And I think this is the interesting thing, that if we take our research aside, people take these technologies and they, if it's a productive relationship, you know, if it does something good for them, it's often outside of what we necessarily designed, right? So that was the big thing, like with all of the intelligent assistants, that people are using them in all kinds of ways that are surprising. Of course, those data are being collected. So that's another thing, but it doesn't seem to stop people. Oh, I like the young attendee of the workshop. I like that. Hey, do you have a question? Ask me a question. Oh, that's so cute.
No, so you can hear you on the speaker. Yeah, it's my daughter, Gita.
Oh, nice to meet you. She's cute. This is what I've loved about this, the Zoom thing. One thing I noticed is sometimes people will have infants, like babies. And, you know, this is the best thing. Like if you bring a baby, everyone's just nice. No one can be mean to the person who is holding the baby. It's a very powerful thing. People should use this, you know, as a strategy. Oh, I have a baby. You've asked a hard question, but look at the baby. So.
I had a quick question. So like for instance, you've worked with a lot of, I guess, multimodal data when you're, I guess, predicting engagement or turn taking. And a lot of literature says that non-verbal and verbal information contain redundant or complementary information. So that leveraging both aspects of these, I guess, non-verbal and verbal information are important. But as with more like machine learning models, like getting these intermediate features serves as a big bottleneck when you're trying to, I guess, predict all these things. I'm like, I guess, stuck in this point where, is it important for us to learn I guess, faster algorithms that are able to extract these intermediate features so that we can use the entire set of all features that's available from this interaction setting? Or is it important to identify which features are the most like contributing to, I guess, let's say engagement or these specific tasks? So I want to get your insight as to what do you think is the path right now? Is it being able to have better algorithms, or is it being able to identify specifically which features are important?
That's a really, really good question. So thank you for that, because the answer is not simple. So the answer is that if we could characterize which features matter in some general way, then obviously that would be the path, because then you would know. But it varies tremendously. So just look at this most recent thing that we just did on gender, right? So, you know, it turned out that the auditory modality was very powerful, but if it was neutral, then clothing made a lot of difference. Now, that's interesting, because this auditory bit was actually counterintuitive relative to something that an earlier student of mine, Emily Provost, did in her early work. She's now a professor at Michigan, so she is not doing this anymore, but she did some work to look at conflicting stimuli. So if I, for example, show you a face that's smiling, but it says something really mean. So we were looking at audio versus visual. And she found that the visual modality was much more powerful in what people perceived and in the affect that it induced, right? If I smile and say something mean versus if I frown and say something nice, which by the way is really hard. And actors did this and like whatever. The actor stuff I always take with a grain of salt. But it was interesting that in the context of affect, when you have those two modalities, it was the visual that was dominant, which is kind of, you know, you figured that like, oh my gosh, more of my brain is involved in visual processing. So that's why. But then when we looked at this gender stuff, we found that the audio was actually dominant in certain contexts, right? So to your question, if we could characterize it and we understood which modalities were key in which context, well, then we wouldn't need them all. But we can't do that in a general way. So you kind of have to do both, you know, you kind of have to do both. And then you add the layer of personalization. And I think that's always why it's important to look at the full data, because, well, even like the developmental literature is another obvious case, that what modalities matter changes over the developmental trajectory. So again, you know, but even there, we don't know for sure, right? Because it's not like, I can't segment. I can't say, well, if your child is 6 months, we're going to stop looking at the legs and now we're going to move on and look, because it's not. It's like 6 months plus or minus 6 months, you know? So that's the problem. So I don't know if does that make sense as an answer, that there is no simple straight answer?
Right.
But that's the purpose of getting a bunch of data and really analyzing it both ways, because you're always trying to characterize the problem in a sense. But I am always skeptical about these specific characterizations because they are so personal. Let me give you another example of that. Again, I said I've been really, really interested in looking at anxiety and depression. And so we're looking at the people who do, you know, characterizations of brain states with like EEG and other sensors, right? And they're trying to characterize something like definitive about brain states. And then of course, what are they finding? That it's incredibly personal, right? So maybe that is really ultimately the answer, is that you do need all the data. You need to think about it in terms of context and individual. And I know that's the worst answer, but.
Thank you. That was super insightful. Thank you so much.
I have a follow-up to that, actually, personalization. I know we are sort of out of time, but I'll just squeeze in my last question.
Thank you.
So with personalization, I think you mentioned that there was an issue where if you were using multiple people and use their behaviors, right, and all that, it was not easy to generalize. Yep. And I'm curious why, because sometimes these behaviors, they have a common aspect. Maybe it was because of the data or something else, but I think that's what my question is really.
No, that's a really good question, but it's very counterintuitive for people. But for certain disorders, like autism is a specific instance of this, where every individual has like a constellation of symptoms and severities. And so it's like everybody's a point in this really high dimensional space. And it's really, you know, you can kind of cluster, but that you're not clustering in any kind of dense enough way to generalize across users. And now you throw over that the complexity of context. So someone like, you know, you take an individual child and they tend to have certain behavioral tendencies, but then then there are a bunch of other things like, oh, are they tired? Are they particularly angry? There's all this like hidden state, if you will. So it's just really, really hard. Out of context would be one thing, but with context, it's a mess. And so again, not like that for everything. Like I said, with deception, we were able to do some really nice stuff that generalized, right? So I think it depends, but it's a very different phenomenon from something like autism. And this goes back to characterizing the population and the use case. And that's just hard because so few people are working on these real problems. And it's like throwing darts in some massive space. It's like, oh, I'm going to look at this one. And I'm like the only one. And this is why we need more people so that we can start to get more data and to understand things better. But autism it's really interesting because it's such an extreme case. I think it puts a lot of things on trial. It's also really compelling because it affects so many people, like 1 in 45 kids now. So you can't just say, oh, well, it's this one thing, but we'll ignore it, right? But yeah, it's a mess.
Yeah, I mean, that makes sense. I think all the things that you talked about today sort of had some sort of connection, which is really cool. And I think he talked about how people talk about going from simulations to real, like virtual robots to real robots. But I think what I did not understand before was it is so hard to actually collect data in real world situations, which is like another step further. So that was really insightful to hear. Thank you. And thank you for the talk.
My pleasure. Thanks for the great questions, everyone.
So now we'll move on to Hayvon Park.
Hey, great to see everyone. And Maya, thank you for an awesome talk as always. I had like so many things I wanted to add, but I tried to remain silent so others can ask questions. But let me first share my slides and begin there.
So,
yes, please. Sorry.
Of course. I had a short intro for you. So Hayvon Park is a research scientist and a principal investigator at the MIT Media Lab. And her work is applied to a range of real-world domains, including early childhood education and healthier aging. And she also had co-founded a startup, robotics, during her time as PhD student in Georgia Tech. Personally, I have really enjoyed reading her papers, which focus on 2 key socio-emotive challenges in AI. The first one is personalization. I think that's what Maya also talked about a little bit. And also the other aspect, which is sort of like long-term learning, which I think Hayvon will talk about today. So I'm really looking forward to it.
Yeah, thanks for an awesome intro, Shataya. I think this is a really good talk to present after, especially Maya's talk, because we overlap in the social robotics field, but also in terms of what motivates our work and what impact we want to make with our research. So today I will talk about relational agents, what we call relational agents, and how we are designing and making impact using these agents in a long-term setting in the real world. So I've been at Media Lab for the past 6 years, and it was quite a journey. It's an awesome place that enabled me to really put robots in the real world and study them. And so when we think about agents, right? So like I listened to the talks from the beginning today, and I don't think I need to motivate the current audience on why embodied agents are important, because everyone is literally working on embodied agents. But embodied agents, like unlike just chatbots, they have like very, very distinctive characteristic, whether they are virtual, whether they're physically embodied like robots. When there is this embodiment, people like to prescribe roles to it, for example. And they have like a certain like work and task objective that they want these agents to fulfill, right? So these agents are with purpose, right? And it's interesting, like once people prescribe a role to these agents, that's when certain relationships start to form. Some robots that are in public places, like in the hotels, in the airports, like in the warehouses, even these robots that don't necessarily interact with the same people over and over again, still they are being there, like fulfilling certain tasks. And within that short time period that people interact, they kind of form a relationship. So relationship is kind of prescribing the role to the agent, but also kind of prescribing a personality to the agent. And because of that, people like build expectations towards these robots. And they also, based on that expectation, sometimes, you know, the agents like fail the expectations, some like success, some succeed. And from then on, as the interaction goes on, what's really interesting is that relationship also changes over time, right? So how in the perspective of designing for these agents now, then, like what do we need to think about, right? Like, because like it's one thing to design an agent that can fulfill a task successfully, but now if the task itself is highly motivated by the user's engagement, like Tim Bickmore's work using virtual agents, helping certain like medical regimen adherence when they're first discharged from the hospital, the adherence and the longevity of the interaction is very important, right? So how do we support those like cases to support users in a more long-term and more successful relationship building, and you know, going forward from that, right? So let's talk about that. And I do want to talk today about like kind of like the impact we want to make with these relational agents, right? So a lot of the times we are so focused on building realistic agents, you know, like realistic animations and realistic looking like physical robots, like they're like movements. But what we don't think as much is like how people perceive it and what impact that makes once you try to intentionally give like the intent of what the agent is trying to achieve, right? So there are some unfortunate examples, right? In some cases, because like a lot of the cases in this example, Sophia, one of the most famous robot in the world, right? It was like it was the first robot to given a citizenship from Saudi Arabia, first robot to get like first artificial agent to get a passport and things like that. But it's like it's really cool technology, right? Like Hanson Robotics is like top of the world in terms of building just physical robots and like the animation, like physical animations. But then when we present these technologies to the public, right? And just beyond the entertainment factor, what impact can we make to people, right? So this video is like one of the most seen robot videos on YouTube. Like I checked today, it just had like 17 million views. This was a video from 5 years ago when Sophia made a joke about, you know, I will destroy humans. And, you know, you can go ahead and look at all the like responses on YouTube channel. So we gotta really think about what is the objective of building this like very believable agents, right? Because like when the agent becomes more believable, then, you know, like people trusting them, trusting what they are saying has an impact in that, right? So I think we are very focused, though we are focused on like evaluating AI algorithms in the sense that we compare to like baseline models, like report out our accuracy, recall and precision rate, like F1 scores. But at the same time, we got to think about and evaluate towards this new dimension of what impact the agents are actually making in terms of impacting human lives. So not just social robots, but I think there's a high impact in this like social agent technology in general. So right now, like we have like smart speakers that have been, you know, very deeply embedded in our lives now, like Siri, like Alexa, and they are very useful tools, right? Like I have to be honest, I actually love my Alexa. It helps me tremendously around the house, like automating things. But we can definitely do more with this socially relational agents. So I think the next step in terms of our field, the next step we can go towards is actually providing like as a motivating ally and as like a emotionally bonding companion kind of technology that can actually bring us to like the next level, right? Right now it's a useful tool to like help me maintain my schedule and things like that. But now if I want to achieve something, if I want to achieve a healthier lifestyle, if I want to achieve like some education support for our young growing kids, or want to help my parents who are now becoming like 80 years old and over, right? So how can we use these agents to not just like solve problems we have, but be a kind of a step up technology that can help us motivate ourselves, like become a ally that can help us achieve in the direction of things that we want to achieve. So this like the concept of companion AI that I like to propose today is really involving like our holistic capacity, right? Not just our cognitive functions, but also our emotional side, and also like really improving our social side as well as our physical side in terms of motivating us to like physically interact or physically move more. One of the core areas I've been working a lot on, and as why I had motivated why this field is so important, is supporting the early childhood education, right? So at this young of an age, children don't learn things by trying to read and write, right? They learn things by interacting with others. They start by, like interacting with their parents, their siblings, then when they go to daycare and school with their peers and teachers. So in that notion, no technology can really support these young of an age kids, unlike these social agents, right? So how can we present these learning partners, like AI learning partners, as a friend who can help like achieve things in their education, so they have like enough preparedness when they first enter the school. So when, especially in a country like the US, when kids enter a kindergarten, they are a very unique sample of their cultural background, right? Like children come from many different backgrounds. So their school readiness in terms of, especially towards their language and literacy, is very different. So how can we support that before they become first graders? How can we support their school readiness, right? So if we look at this graph of inequality in education, the gap, the intervention that you need to make, the investment to return ratio is the most highest in the earliest years. I mean, we can of course guess that, right? And it becomes even harder as children grow and as they get to like high school and post high school. It's hard to really make impact in their education. And like I said, the reason social agents can play a big role here is because learning is innately cognitive, social and relational activity, right? There has been very motivational work from John Gabriel's lab at MIT, who just a few years ago learned that it's not just about how much word kids are exposed to at a young age that really influences their future like language and literacy skill, but it's actually the turn-taking interaction they have, like conversational turn-taking, and quality of those turn-take they have with their caregiver at a young age. So it's not just about number of words, but it's actually about the interaction. So we are very highly motivated in that aspect. So I'm going to show a video of one example of how even like an AI agent and children perfectly understand robots or AI agents, like Maya said. And here I want you to focus on how kind of like the theory of mind in these like young children already works out towards an artificial agent.
Nice to meet you. Want to play a story game? Yes. Once upon a time, a little penguin named George lived in the South Pole. Go ahead, just tell a story. I want it to be about a snowman. Ooh. Once upon a time, there was a snowman, and he was alive. I'm a baby dragon. See my wings? Yeah. Will you play with me again later? Yeah. Ooh, hi. Hi. Remember me? I'm green. I remember. Is it your favorite game too? Yeah. Put a penguin with a backpack and put it on the snowman's head. The end. Your turn.
I'm gonna tell a story about a snowman.
Ooh.
Once upon a time, there were two penguin sisters.
So I wasn't part of that study shown in the video, but it was like a study done before I came and joined the current group. But it was a very interesting study because like you're probably wondering, but this study was like conducted by Jacqueline Corey, the previous PhD student at Media Lab. The robots like audio and those things were pre-recorded, so no, TTS is not there yet. But it was really interesting because this study like really shows like how children interact. So it was a really great analysis on how children like perceive the robot and interact with the robot in a core storytelling interaction. So storytelling is a very interesting like scope domain because it gives the agent a chance to it gives the chance for the agent and the child to like take turns conversing, but it's not like short conversational turn. It's actually more like a longer turn taking, like telling stories to each other. So there's like a more chunk of text we can analyze. And, we can also analyze not just like the text that they're speaking, but also like how they are speaking it and also like how they are emoting while they are speaking it. So from this data, like I had like later on trained more like personalized models, how to really enable this as an automatic interaction of autonomous interaction. But what was really interesting and what we see over and over again, and part of why I already talked about this, is that people, when they interact with social agents, their mirror neuron like activates the same way when they are interacting with another human. And some studies show that this is more prevalent when people are interacting with a physically embodied agent like the robot, and how like people's brain is like programmed to do it. So this like was really interesting because now if like people can be influenced by the interaction with social agents, that motivates us to think how we should develop the interactions, right? It's not just about the perception technology, it's not just about generating believable animations on the robot, but it's also about what do people gain from the interaction and how can we predict that and model for that and use that to the benefit of the user. So I like to motivate in like the 4 fields that I've been currently working on. So first is definitely the perception, like how can we perceive and understand human cues? So this is multimodal and cross-modal by nature. So like when people speak, it's not just about the text they output, but it's also about the prosody in the speech, how they talk about things, but at the same time, how do they use their nonverbal features to communicate? And it's also then important because for the embodied agent, it is also important that the robot is able to communicate its own mental state, right? So it needs to use like the same cues that people use because those are the cues that people understand. So how can we generate those expressive cues that expresses the agent's intent and the mental state, right? So then over time, through the interaction, how can the robot learn and personalize to the person? And then lastly, how can, because now people, like I said at the beginning, because people prescribe certain social role to the agent, and as the relationship changes over time, how should the agent establish a social dynamic role and adapt to the perceived role that users prescribe to the agent, right? So the last area is like very new area that we just got into, but it's like, I think it's the most exciting area in this domain. And the core thing here is now we're also looking at not just building these models for specific interaction, but as a kind of like a lifestyle companion, how can the agents adapt to users over time and across interactions, right? So I'll be talking about that. So there's like a very specific projects that I like go over if you're interested, but I won't like go to details. just forgot to hide that slide. So first topic I do want to talk about is understanding and communicating mental states. I think today we talked a lot about this topic. First was, generating so because robots have this embodied agents have embodiment. They need to generate these body gestures and nonverbal gestures along with when it's is communicating, when it's generating speech, right? It's just not about TTS, but it's about the auto generation of motions that these agents should produce, right? So this work was, but the problem here is we have so little data to train good, because also the robot's embodiment is so difficult. A lot of the times we do transfer learning from different embodiment to this robot specific embodiment. But again, it's very, very, very sparse data that it was really hard to kind of have a data set where for this specific robot type, when it speaks, what animation it should produce, right? But then at the time, another group at Media Lab came up with this deep emoji work where they trained the tweeters with accompanied emojis and learn the association between them. So this was kind of a sentiment model, but it was more effective in terms of, it wasn't just outputting joy 90% or sadness 20% kind of a scale. It was actually outputting more emotive expression of emojis, right? So we transfer learned this model to how we had inserted the robust animations in when telling stories, like you saw in the video earlier. And then so we transfer learned to this smaller data set that we had and generated this model that I would say was quite a successful project. And here are some examples. And one for the negative sentiment. So, and then the dots you see here, those were to evaluate the range of motions, because we adapted the range of motion as a level of expressions and level of arousal of the agent. So this was now embedded into our new storytelling study that I'll talk about a bit later. But then another project is also then understanding how people encode and decode different social cues. This particular project is really about learning how children at this young age, at the kindergarten age, use back channeling cues, because back channeling social cue is one of the last developed skill in people's development. So people only right now, as adults, we use a lot of head nodding. But if you have young kids at home, I think Hannes, you said your door, someone said their door is 7 years old, I think. Sorry, I forgot who it was. But yeah, so look at how they back channel. Children, especially at this kindergarten age that we did a data collection on, they rarely use head nod. They use more verbal responses and gaze.
So the cat broke the window and then it ran through school and peeked inside. He saw cat saw classmates.
Yeah, and then we annotated for when these cues happen, also using Elan, and then built this content estimation model of how the speaker cue kind of influences, how the speaker's cue influences the listener to back channel, and how that back channel also then influences the speaker to kind of do these observation kind of cues. And then we apply this to an agent. I'll skip this one, but I'll talk about the next study we did. So we developed a back channeling model for the robots, and we placed 2 agents, and we introduced children that, these are baby robots and they can't speak yet, but they love to hear stories. And so we asked children to tell stories to the 2 robots. And of course, like one robot was using the back channeling model that we had developed, and the other one was using just like an average of back channeling that children do when they are listening. The interesting thing here is like we analyze what things that children can encode in their behavior, but also analyze if they can understand, they can also decode those cues from other people, so other agents. And we actually have some interesting result in that regard. So here's a video.
Then I couldn't breathe up in the air. And then the Einstein workshop that I've been to, that there's Lego We-Do that they do.
So when we analyze how like children like gaze at the agents, but also which agent they direct their storytelling to, we saw that children actually gaze at both robots quite equally. But then when we analyze it further, children actually directed storytelling to the more contingently back channeling robot, but they looked at the other robot as much when they are not doing a storytelling. So when we interviewed them, they said the other agent was distracting, and that's why they had like stopped storytelling and gaze at them. And further interview revealed that children, when the agent was using nodding as a decoding, as a back channeling cue, there was a very big spectrum, even across like this the same age group children, which is like 5 to 6. Some children like understood that as a back channeling cue, that they are being attentive and listening to their story, versus some children actually thought the agent was distracting them. So this is just motivating more and more why personalization is so important, not just in terms of the high level interaction behavior, but in terms of like generating the animation of the agent as well. So in terms of personalization, I've been working on this domain for in many different dimensions. One of the core personalization dimension that I think is very important is the role of the agent. So like I motivated earlier, the role has very big impact on how people perceive the agent and how they build relationship. And there hasn't been much work in terms of personalization. There's been a lot of work personalizing the educational content, the curriculum. There's been personalization in terms of like the robots like dialogue, behavior, but there hasn't been much research looking at how the role can be personalized. So I think especially this type of work is very interesting. One work I'll introduce very briefly is we worked on this growth mindset project with a psychologist. And it was about using the agent as a psychological study tool, like how if the robots are projecting more growth-oriented mindset, will the children pick that up? And also would that influence their own mindset, right? So just give a quick intro. Growth mindset is about believing in your ability that if you put enough effort, that you can succeed. Like fixed mindset is you think you're born with certain ability that you can't really change. So like, for example, like I'll never be a football player because, you know, no one in my family is a sportsman, versus, you know, yeah, maybe I won't be a professional player, but the more I try, I'll get better. And that's what matters, kind of like different mindset, right? So again, like that mimicry like happens so deeply in children when they are interacting with the agent. So that social influence and emulation during these interactions were really powerful. What we did here is though, we adapted the robot's behavior. So the comments the robot make and the frequency it makes was according to how we assess the current state of the child's growth mindset. And because of that, the interaction became less tedious for children and it improved their engagement. So the underlying algorithm is similar to this study, so I'll talk about it in kind of the same framework. And this work was also about the robot's role adaptation in terms of when should the robot scaffold? Like should the robot also then ask help from the child so that the child can also, you know, demonstrate their knowledge, but at the same time help the robot out, which in return really improves like their motivation and engagement in the task they are learning. So this is a vocabulary game, like an I Spy game. They're trying to like find the object that is given by the game system. And I think Hannes was asking this question about like data collection here, because like we like to use the tablet, like another like, you know, shared workspace between a user and the robot. And like what Hannes has suggested in terms of, you know, like keeping those like trust and relationship with the agent, but doing data collection on like a secondary device. We are when we're designing the systems, you're kind of like doing that because data collection happens on the tablets, the installed cameras and things like that. So when we are sending these systems now, we are sending this to the homes, as you can imagine. And then we give like the parents a choice to make, because we tell them the only data collection that happen is with like this webcam that is installed as an external camera, and the camera on the tablet, also the microphones. So if you are not opting for data collection at any moment during the study, like this is a button you can press to prevent data recording, but the agent itself is not holding any data of like, your conversations with your child and you know whatever it did with during the interaction. So that worked really well, because we also learned that, especially when we start to send these agents to the homes, people had a lot of trouble with the cameras and microphones. So yeah, so in this case, the child was interacting with robots that dynamically changed its role based on assessing for the child's engagement as well as the child's learning progress.
I'm lavender. Oh,
what are we trying to find?
We are trying to find lavender color stuff.
Okay.
That's
the word was lavender.
Yes. And what is lavender though? What's lavender? No, that's blue. What is lavender? Girl, jumping.
I'm sure you will do better next time. I believe in you.
Robot's turn.
Time to perform. Lavender is purple.
Yes. Just like my friend loves lavender. Ooh, that's orange.
Flower.
I believe.
So in this example, the robot's taking like a more knowledgeable peer role in this case, because the child was having trouble understanding what the word is. So by demonstrating and providing scaffolding, the agent is helping the child out in this example. The interesting thing is, the reason I selected this clip was the mimicry that happened between the child and the agent, right? Like when the robot encourages the child encouraged the robot back in the same way, right? And that nonverbal behavior where the child leans towards the robot, when the robot leans towards her, all that kind of interaction like helps, and especially the dynamic role switching really helps the perception towards the robot and relationship building with the agent. So here, what we are doing is we are basically pre-training this data on with a pilot study interaction, where children actually did this episodes of games with a random role selecting robot, and then from that we observed how the children's engagement state, and as well as their time to select the next object and the correct and wrong of the selected object. We are giving the reward back to the agent in terms of the child's performance and engagement. So then during using this seed policy, then during the interaction, the robot is able to adapt to the specific child's interaction over time. So when the child, the agent basically learns when for this particular child, if this child's engagement drops when robot steps in, then robot learns over time, even though the seed policy tells when children fail multiple times, it's good to the robot to jump in. It'll actually learn for this particular child that, well, I don't want your engagement to drop, so let me step back a bit and let's see how your engagement changes, right? So it's kind of the intuitive reinforcement learning algorithm that we implemented. That worked quite well for the role adaptation. And it showed in terms of their educational outcomes, as well as retained knowledge after we came back after several weeks after the study. So we compared it to a fixed role robot. Like, for example, if the robot is always a less knowledgeable peer, always asking the child to help, versus the robot that knows it all and, you know, always tries to help the child, and the adaptive case. So the vocabulary assessment showed that at the beginning, the pre-test, there was no difference between the conditions. Immediately after having 2 sessions with the robot, children show like significant learning differences between the 3 conditions. And then that kind of like that trend stayed after 3 weeks when we went back. And so this was like a highly motivating study in terms of how we change the agent's role accordingly to how people engage over time. This was another study that I told you about earlier that kind of incorporates the back channeling behavior of the robot that is adaptive to.
Hi, my name is Tega. Nice to meet you. What is your name? Aliana.
Early literacy skills form the basis of a large part of children's future learning. But children entering preschool and kindergarten come from linguistically diverse backgrounds, affected by many factors, including their family's cultural origin and socioeconomic status. Therefore, it's important to create personalized solutions for promoting early literacy.
What was your favorite story so far?
My favorite story, it was the bunny one.
Using a social robot as an embodied AI agent provides several advantages. Studies show that early literacy development requires exposure to a rich variety of spoken language and vocabulary during social interaction with others. Children engage with social robots in an emotive and relational way, and the affective cues that social robots can elicit from children provide a better opportunity to assess their engagement states. Our reinforcement learning personalization policy takes full advantage of these engagement cues.
So I'll skip this part, but we engaged with 67 bilingual second language learning children in terms of using a storytelling context that we love to use for the conversational interaction when designing conversational agent interaction with young kids. So basically here again, we are looking at the learning progression as well as the engagement of the child to reward the robust actions. In this case, the robust actions can be like the difficulty of the storybook it selects, also the difficulty of the sentences in those books and what question it asks and how to ask the questions also. So when the robot is adapting based on the child's engagement, it'll actually try to, so the learning progression and engagement kind of like works together in terms of bounding each other, because when we didn't really have the engagement factor in the reward function, the agent would often select a more difficult storybook just because there's like a lot more things that the child can learn because there's a lot more information in it. It'll sometimes, converge to selecting a more hard story, versus now if we look at engagement, how children engage with certain storybook, the agent can now more intentionally select the right bound of the difficulty level of storybook, but also the topic of the book, because then when there are several selection of books, it can prioritize the one that it knows the child will more engage. So again, here we see that personalization effect was very high, and that we also analyzed for their engagement. And so when the agent was personalizing to the child based on the engagement, we can see that in terms of their facial expression, they are more engaged. We also measured their engagement in terms of like a physiological sensor using EDA sensor. And we could actually see that they were more attentive when they were interacting with a personalized agent. I won't go into details, but we then, like I said before, children's like verbal cues and nonverbal cues are very different at this young of an age. So it was like really important to understand their personal level of engagement cue, like how they exhibit the engagement cues. So we developed this active learning approach to it because it was really hard to just determine their engagement level using available like facial expression extraction algorithms like Affectiva tool. So we actually developed this tool for the experimenter, or it can be a parent or teacher, to give labelings as they are observing the engagement with the agent and during the first session they are having with the robot. So we are now deploying these robots like everywhere, literally. This past year, we sent many of these stations to the homes, and some of the families are still holding on to them. And we are collecting data on how families are implementing these stations at homes. So like here, as you can see, like I mentioned earlier, we have like all the data collection tool in the part of the tablet and the computer, a part of the station. And for the agent, it's just focused on providing the interaction and not doing data collection when they are implemented in the home settings. The interesting outcome outside the algorithmic performance and like the learning outcome from children, what we learned was that when we analyzed we asked like self-report and behavioral analysis of how children perceive the robot and how children rated the robot in terms of what relationship they think they are having with the robot. We could see that when children reported of having higher bonding and working alliance with the robot, they reported a higher education outcome as well. So this is actually not a very surprising observation when we think about psychology literature. When people talk about that social like support and bonding they build between therapists and patients, how that improves the outcome of the therapies, and even like finance decision making, how like relationship influences like their decision making in terms of investments and things like that. So we are now applying this concept. We're trying to build like an AI model to analyze for relations that people build with the agent and to try to like basically dynamically learn to change the robot's behavior during a long-term interaction in a healthcare and well-being setting. So one of the interactions of the study that we did was interesting because Maya talked about like deploying robots in the dorms, which we actually did. And like this project was supported by the health and mind and health funding at MIT, because our undergraduates' emotional wellness like drops significantly over time, like from the day they enter school and as they progress through their program, their emotional well-being just like drops, and like the number of students who have to take a break is increasing, right? So we were really hoping to make influence on helping students build resilience. And this was a project that we were motivated by, and we worked with a psychologist to come up with a protocol. And we sent the robot for a month to each student's dorms, where they interacted with the agent for 7 sessions. And each session, the agent delivered a emotional wellness coaching. And we then analyzed like what effect it had over time, because during that time, students have like many exams, and the prior literature report how their emotional wellness like declined throughout the semester.
How's your Thursday going? Coming. Oof. My day is going well, despite how it might look. Yeah. Like. I really appreciate you sharing that with me. Yay. Today we're going to do an exercise called 3 Good Things. Research in positive psychology shows that cultivating gratitude can benefit personal well-being. I'm thankful for getting to be in your nice room. Being out of the lab is a good change of pace. Your turn now. Tell me 3 things that you're grateful for today.
I'm thankful for being able to catch up on work that I was behind on over the past week. I'm thankful that my parents are having their 20th anniversary this weekend. Or, well, they had it. It's today, actually. And I am thankful for the good friends that I have in crew.
That was awesome. Gratitude is an important skill to have. It can improve life satisfaction by allowing you to see things from a different perspective.
So as you can see, the method of delivery of the robot sessions was like quite coach-like, right? So here, like with this project, I want to like talk about like agent personality, right? Because it's a big part in social animation of social agents, right? So yeah, we did see improvement in well-being across all the participants before and after, but what we focused more on how students' personality was affecting the outcome. So we saw that when students reported of having higher neuroticism feature in the Big Five trait, their response to the sessions were much worse than students with reported high conscientiousness. So now we are trying to think about ways to change the robot's personality based on the user, right? So we did a lot of like literature survey on how to provide more effective therapy sessions to people with high neuroticism. And some literature pointed out that, you know, like building rapport prior to the therapy sessions is especially important for people with high neuroticism. So what we are doing now with the deploy study, we sent the robots, it's a longer study, and we plan that the first initial weeks are just robot doing, because now the robot we are using here is Jibo, which has like some conversational like features and like fun entertainment functions. So we just let them play with the robot for a week before they start the therapy sessions. And we are trying to see if like that helps with the outcome of the therapy, but also they say like the self-report, like self-disclosing of the agent is much more helpful in terms of building, you know, more adherence with this particular participants. So we are now trying to kind of like balance those and see if like those that personality change in the agent has an impact in people with different personalities. And also within this study, we also saw that when we did a qualitative interview, students reported of having a wish to have like better conversation with the agent, right? Because yeah, if you think about all these smart agents now, like remembering conversation histories and building upon that history is just non-existent. It's really hard to achieve, right? I know a lot of people are working on this domain, but it is a crucial function, right? Because people, especially when there's an embodiment of the agent, people prescribe a role and relationship with that agent. So when the agent now doesn't remember things that you just talk about with the agent, that their disappointment that's the highest reason for their disappointment with the agent and where the relationship breaks with the agent. So we just embarked on this project on how to generate next utterance with the agent based on conversation history. What we are doing is we take like the base model, and then we implement this like MRF chat, which is like selecting out of the like utterance generated candidates. Can we actually select an utterance that is much more relevant to the history that it had with the user, right? And we did an experiment on how like the length of history that the agent records when generating utterances, as well as how the relational information affects the outcome of the generated quality of the utterance. And so we evaluated this based on human evaluation as well as automatic evaluation. So basically the agent has this like model of its own knowledge, and now it builds a knowledge representation of the user as well. And when things like now we're trying to find overlapping things between the agent and the user, but over time, as the conversation goes, it will update its graph based on the related concepts that appear in the utterances, right? And from that on, because after we build this representation of like shared knowledge, we use this to select a better response from the base model, the utterances that the base models generated. And I'll just quickly just go to the results. And we found out that when incorporating a more conversational history, that our proposed like MRF infused chat generation model was actually highly rated by human evaluation. But also when we did an automatic evaluation with the data set, we saw actual like more high performance when the conversational history is, more conversational history was incorporated in terms of generating the utterance. So where we are going here from then on, I'm sorry, I'm just like going through the slides because I know the time is like up. But here is how we are going to design the agent's personality, but then also building his persona and incorporating that into the more relational dialogue generation. Right now, we are mostly focusing on the conversation it has with the user. But like I said, when for some users, the most effective interaction happens when the agent also self-discloses a lot. So that means they're expecting the agent to also have like, so agent is basically a character, right? So they want to learn about the character, which means that the agent needs to use this like knowledge field to generate these utterances. I will end it here before going to the next project. But so this is kind of like wrapping up as how we should build the interaction and how we should, the way to go towards building a relational agent. And also in terms of building relational agent and evaluating them, we should evaluate them in the real world context and what impact it makes in people's lives versus just how cool AI algorithms are. Thank you so much.
Thank you. That was a really cool talk. There's a lot of interesting work going on there. If anyone has a question, we can spend a few minutes here, although we're slightly above time, but I think we can spend at least 5 to 10 minutes for questions.
I was just thinking about the ways that you kind of break the bonding, and you talked about, this last point is very interesting about like how much the agent remembers and things like that. So you kind of have to avoid these specific things that completely destroy the illusion in a way. And you also talked about the personality of the user maybe being a part of this. I'm wondering also if the personality of the user makes them more or less ready to kind of maintain this illusion. I mean, if there are certain types of users that, you mentioned the conscientious ones, maybe they just want to play along a little bit more than some other users, and you've maybe figured out that some of them are just like, they love the illusion, or they love the role play that takes place. So anything you even try on the other people may not work out because they just are not ready to buy into this. Is that something you're considering?
Definitely. I mean, we see that all like every time, right? So there are people who like to play along. They are usually people, that have some kind of illusion of like an artificial agent. So when an agent arrives at their home, they are really just enjoying the experience and exploring what the agent can do. And those are also people who understand technology well, right? They know technology, like they have used Alexas before. So they have certain like right level expectations in that regard of like how much conversational capability an agent can have. But not all people are like that. So when people have like higher expectations, that especially breaks very easily because they have high expectations when there's like a physical embodied agent in front of you versus just a speaker or like an agent on your phone. And that happens all the time. The one way we do is we talk to people, we give an intro of the agent. I believe Maya did this work on giving backstories of the agent before, getting onto like the main study. So that is very important because it helps put people's expectations in the right place. As well as, but like I said, the conversation, the agent not remembering things that it's shared with the person before because, the conversation modules are different from like one skill to the other and they don't really connect. Those are still the very big frustration points, regardless whether people have the right expectations or not, right? So that's why we are embarking on this new kind of like conversational method of incorporating conversational history, which is popular domain in NLP. But what we are doing on top of that is because these are embodied agents, now we need to also incorporate the agent's persona to the conversations, right? So it's not just about, generating relevant information in the next utterance based on conversation history, but it's also about incorporating those persona in those conversations that what we are working on. We haven't gotten to that point yet, but we're trying to like mesh the two knowledge graphs together, basically. Yeah, I see Maya's hand up.
Oh, I think it's, first of all, I think it's wonderful work. As you know, I love this stuff. It's so obviously we're in the same headspace. So, and I did see the paper about the dorm room deployment. I was really impressed. I'm really curious how you're gonna go about modeling personality, because you talked about neuroticism, which is this dimension that it's not obvious how, because we know that obviously, our past work showed that matching the personality of the agent and the user makes the users engage more and learn more, etc. But we always focused on the extroversion, introversion. When it comes to neuroticism, right, it's difficult to think about how you would model that dimension. And would you want to? And everyone always makes this joke about that. What was that, Marvin, the robot from Hitchhiker's Guide that's always depressed, right? But I mean, how do you think about modeling these other dimensions? It's not obvious. So that's kind of an open-ended question. I know we don't have much time, but I'd love to hear more. And you and I can also connect.
Yeah, definitely. I'll just quickly answering your question. So we adopted to the Big Five trait, and we actually analyzed people's, our students, our participants, outcomes based on all different personality dimensions. And what we found was there was a significant difference between these two groups of students. So with high conscientiousness and high neuroticism. So that was the one personality dimension that we found significant outcome differences. And so we did a lot of literature survey. We consulted, we're working with a psychologist who's expert in this domain. And so the two dimensions that we implemented this time in a new study is to give them enough time to understand the agent before we start the intervention sessions. So them to fully explore the agent before the therapy session happens, which will also help with setting the right expectations. Second was we made that agent particularly do more self-disclosing. So we haven't analyzed the outcomes yet, but it'll be really interesting to compare with our previous data. So we've just returned, the robots just got returned, so we're analyzing the data now. Yeah.
I am so impressed, by the way. Just kudos for deploying in a place as challenging as dorm rooms. Again, people need to be doing these brave studies. So all thumbs up to you.
Yeah, thank you so much. Yes, the lighting condition, everything is so bad. What we did was we actually borrowed human intelligence by showing a small thumbnail of their face when they are interacting with the agent. So they can have their sense of how good the lighting is, if the camera can actually see their face, and if they are sitting in the right location and things like that. Yeah.
Brilliant. Great job.
So I have a lighter question. So I was curious if if the kids like the furry robots more or the non-furry ones.
So that was Maya was actually involved in the designing of the Dragon Bot, which was shown in the first video. So you can see Jibo in this in this slide, but Jibo is more plasticky, right? According to Jibo INC, people who designed the robot, they wanted to go for an iPad look where it can appeal to general population and not just for a specific age group. We thought furry things will be appealing to young kids. Well, and it actually did. They like to pet the robot. They know inside is a robot because we let them pull the mask, see inside. So I can't tell you because we didn't do a study of comparing a plastic robot to a furry robot. But yeah, kids engage with the robot very well. Yep.
And it's not just kids. I just want to throw in that it's not just kids. We've used that form factor for the elderly, and they also like it much better than plasticky Apple-like robots. Sorry, but I gotta be honest.
Yeah, there you go. Yeah, we didn't do any those studies on our end. but awesome.
Awesome. I do have one more question, but I think you're slightly running late. Unless if Stacey doesn't mind waiting for a quick more second for a question, I might just go for it. It's a small one. So
yeah, go for it.
Thank you. So the shared knowledge part, I think the project you talked about just before this, it talks about taking that shared knowledge, creating a graph. And I was wondering if once you create that graph of certain topics, possibly, I'm guessing, I didn't get exactly what it stored, but probably it's a bunch of topics, what they talked about and particular things and just named entities for sure. Would it make a lot of sense if the agent sort of learned more about those topics so that next time they talk, they could like talk more about say a sport, or then for example, they're talking about football, or actually soccer is what I'm talking about. So the scores of the recent matches for the teams, something like that. I don't know, like, is that something that would make a difference, or is that something, yeah.
Yeah, exactly. So we're experimenting like that exact component in early childhood education again, because we can take it and scope it more easily, and children level words are easier to kind of generate like relevance models. So we are actually doing that. So when we find like things that have been like topics and named entities that appear in the user's utterance, the agent will grow that graph using related terms. So our first experiment is within a storybook context with young children. So the agent will first extract concepts from the storybook prior to the interaction, and it will actually expand it. We use like Wikidata, like relation, like search, and do like two-step relation, like expansion of the graphs. Because even in young children's storybook, there's a lot of common sense knowledge that you need to come with that if you just from the text can't really extract. So after the agent extracts like those, expands the graph with those related concepts, then we're generating questions, and Dongwon knows a little bit about this because he's been coming to like our project meetings. But then the agent can actually generate questions in a more rich way than generating questions just on the text that appear in the storybook. So that way, it's better for a question generation, but it's also very helpful for understanding the user response. Yeah, it's just even more helpful for understanding the user response, because a lot of times the response is outside the topic that appear in the storybook text. Yeah, thanks for asking an awesome question.
Awesome, thank you. Thank you for the talk, it was really good. So now let's quickly move on to our last and final speaker. Stacey, if you would like to share your screen. So while he's setting up, a little bit about Stacey, I'm sure a lot of you already know him. He is a professor at the College of Computer Sciences and the Department of Psychology in Northeastern University. I feel he has a unique perspective on human behavior from both the angles of computational modeling and psychology. And it does show up in all the work that he does, which involves human cognition, social behavior, evaluation of these models. So in fact, like one of the first papers that I read on behavior generation was by Stacey, and it introduced behavior markup language to sort of formalize nonverbal communication. And I've really enjoyed like his approach to this problem in general. And I'm really excited to see his thoughts on form, function, and aesthetics. Over to you, Stacey.
Hi, everyone. So I probably will cut some of the talk out just because we're kind of running late. But what I want to talk about today is sort of my internal conflict. So as I was just introduced, so I sort of have one foot in psychology and one foot in AI and computer science. And you see that conflict in all the engineering I do, and that conflict will come out today because there's this whole question in my mind is when I'm building these artifacts, am I trying to be psychologically realistic, or am I trying to get some effect? And you'll see that conflict, and I'll talk a lot about that. And in particular, I'm going to talk about gestures, and particular kinds of gestures, metaphoric gestures, to sort of illustrate these points. Let's see now, is it going to go forward? No, it's not going to go forward. Why not? Hold on a second here. It's playing with me. Okay. Yeah, so I do a lot of work in computationally modeling human behavior. In particular, I worry a lot about the mental processes like emotion, cognition, and theory of mind reasoning. And in particular for this talk, nonverbal behavior. But the flip side of that is I've built a lot of applications over the years. So going back, I don't know, 20 years to an application to help mothers of pediatric cancer patients, the gunslinger application I did when I was at IC.
With computer vision and natural language understanding.
Teaching doctors to break bad news, an AIDS intervention application for some people in the psychology department at USC. The quite famous project that LP headed on basically psychological assessments.
Pay attention, Max. We start
Use of these things in psychological experiments. More recently, an avatar for somebody suffering from motion.
This is a lot easier.
And essentially, if you think about the technology that these artifacts have, is they have some way of like sensing the world. They have some sort of understanding, and then it goes into the quote unquote brain of the virtual human, which at times has included things like theory of mind reasoning, emotion and cognition modeling, and dialogue modeling. And this generates some belief, desires, and intentions, and that leads to some nonverbal behavior generation as well as verbal behavior. Now, the reality is over time, these applications, it's sort of like, they've sort of like become dumber in a certain kind of way. In particular, a lot of the times now when you build these applications, you don't have these sort of complex internal mental states. You have essentially a dialogue model. So it's typically a machine learning based dialogue model. And so really then you're trying to do the nonverbal generation using the utterance text and maybe the audio. If it's a wave, if you have recorded audio, and basically you can do prosodic analysis on the audio. And so really that's this sort of focus of this talk. What are the outputs of nonverbal generation? How it corresponds to these inputs on the right there? And what's the role of automation? Can we learn this generation model, and under what conditions can we learn it? So just to start things off, I'll state the obvious. We're all in this meeting of believing, I suspect, that nonverbal behaviors have enormous social emotional functions. I think in particular, some interesting things that you need to consider is we often think about nonverbal behaviors affecting things like emotional states of the observer, or having in a sort of an emphatic focus, but in reality, they also convey meaning. They can impact memory, learning, and comprehension in the observer, and they can carry explicit meaning at times different from the verbal channel. And so I'll talk more about that as we get further into this talk. And of course, there's been the cottage industry in the virtual human community of looking at essentially, do these effects happen when you have a virtual human interaction? So people have studied a large range of phenomenon in terms of, if you manipulate the behavior of the virtual human, do you have an impact on things like rapport or willingness to disclose? And often the answer is, yeah, almost. It's sort of like, it's not the same exactly, usually there are differences, but there's a lot of similarity as well. So what I want to lay out is the complexity of nonverbal behavior. Just how complex it is, because whenever we build an artifact, we tend to focus on a few behaviors But in reality, if you think about what's going on, there's this enormous wide channel of information flowing between two people in a face-to-face interaction. All these kinds of behaviors. And these behaviors, this wide channel exists in large measure because there's an equally wide channel of meaning, internal mental states, if you will, that are actually influencing these behaviors. So of course, there's the regulation of the interaction, the specific conveying of propositional content. There's internal regulation, such as cognitive load that impacts things like gaze. There's leakage of things like emotion, attitude, trait, and culture. And then there's also the perceptual reactions that are occurring that are affecting these behaviors. And this relationship tends to be pretty complex. It's in the sense of, one of these behaviors can actually be used in multiple different contexts. So raising the eyebrows can be used in turn taking, it can be used as emphasis, it can convey emotion like surprise. And also any particular function, communicative function, like emphasis, can be conveyed by different kinds of behaviors. So we have this kind of many-to-many mapping. Meanwhile, all these behaviors are influencing the perceiver of the addressee, if you will, or the observer of these behaviors. And they're making inferences based on what the internal mental state is of the speaker, but also it's influencing their own kinds of cognitive processes, their own kinds of emotional processes. And of course, that's a gross oversimplification because I'm saying a nod is a nod, but in reality, and a smile is a smile. But in reality, we know there's a lot of variability and richness. That for instance, there's many different types of smiles, and we know how they're ruralized matters dramatically. So smile types have different timing, different smiles have different appearances. Ava Krumhover did this wonderful study where she manipulated the dynamics of these nonverbal behaviors, and it showed how it changed observers' attitudes. And the timing is really critical because there's a correspondence between these nonverbal behaviors in the verbal channel. So there's a lot of complexity going on here in a real human-to-human interaction. And I want to kind of sort of like drill down on that a little bit by looking at gesture, which is something that's fascinated me for several years now. Now gesture, as we know, basically has a complex structure. There are various phases of the gesture. And if you manipulate those phases, often you can change the meaning that is inferred about the gesture. For instance, if I go to a pre-stroke hold and I hold my hand there before I do the stroke, that changes how people interpret the gesture. It draws their attention, it creates greater emphasis on what I'm saying. And if I also hold the gesture after the stroke, again, that creates kind of emphasis. So how these things blend together matter. And for instance, if I go out of gesture space and drop my hands, then it's almost like a period. It's almost like the end of the paragraph in gesture space. So the structure, the temporal structure matters. And then of course, there's all these different kinds of typologies people have created. This is McNeil's typology of beats, iconics, and metaphorics. But Ekman has his own typology. Kendon has his own typology of the kinds of gestures or the various dimensions, the various kinds of meanings that you can be conveyed by a gesture. And I think it's important to realize just how complex these behaviors are. So this is a chart on the left from Genevieve Calbri showing the different kinds of hand shapes of gestures. And these things convey different kinds of meanings. So a fist, a bowl, that chopping motion, these things convey different kinds of information. And it's not just that the shape of the hand matters, but it's also the motion of the hand that matters. So for instance, if I want to say somebody is grasping an idea, yeah, I can end in a fist, but the motion of the motion of closing my fist is actually the concept of grasping an idea. And similarly, the arm can be moving in certain kinds of directions. It can be a cyclical motion. It can be a direction towards the addressee, it can be the side, it can be, you know, in these directions. And these directions can convey different kinds of meanings. There's a classic kind of concept that comes out of Delsart of a cube. And Delsart talks about this notion of a cube that's in front of the speaker. And if the, you know, depending on what face of the cube of the palm is on, it conveys different meanings. So this is like stop, this is like pushing away, this is like rejecting something. So depending on which face you are on the cube and whether or not you're moving through the cube changes the meaning. And it also talks about control and support. And it's a fascinating way to look at it, at how these different motions convey very different meanings. Even in the case where the hand shape itself is staying the same. You just have a flat palm. So this leads to the first point I wanted to just, and I'm not making any strong claims here. I'm just sort of like raising these points because they plague me. So the one question you have to ask yourself when you're building these virtual humans, and I presume also social robots, does the input and output afford this motion richness? You know, for instance, how are the gestures acquired and animated? So if, for instance, you have an animator handcrafting animations, you can make the gesture as rich as you want if it's a good animator. But you have a limited repository. Unless you have lots and lots of money to hire lots of animators, you're going to have a limited library. Mocap, in some sense, sort of frees that up somewhat in some ways, but not completely, because mocap data usually is limited also. This may be a single person, and if it's just a single person you're doing mocap on, well, there's immense differences in how people gesture. Some people, as we'll see momentarily, have very rich gesturing. Other people don't gesture much at all, frankly. And so there's enormous individual differences. There are differences, most critically for the applications we build, there are differences with regards to the role the person is playing. So if you study a clinician, they gesture differently than, say, a politician, but they both gesture quite a bit. There's also this question of, if you're doing mocap, do you have the necessary degrees of freedom reliably? And so a lot of the mocap data sets we use for machine learning of gestures don't really have good finger motion, a good hand motion, right? So it's like, it's a real problem because you get this kind of gesturing, and even, you know, this includes, you know, my students working on it. We get this kind of gesturing where the hands are just sort of like these dead things at the end of the arms. And then there's a question of, you know, if you're using something like mocap, are you doing the generation of the gesture frame by frame, or you're just invoking a whole mocap file of the gesture? So there's different kinds of ways of actually getting from the mocap into the animation, which impact both the aesthetics as well as the flexibility, which are often in conflict with each other. But the important thing to keep in mind is that the form and motion carry rich meaning. And to talk about that, I mean, you know, so, there's this great quote from Adam Kendon: the physical forms of gestures are derived from concrete actions, and they serve to express all manner of abstract meanings. So even though we're talking about this physical motion, that they can express very abstract things. And I want to show some examples of that just to sort of illustrate it. This is a video I've shown quite a bit. It's a video of a clinician that I studied in order to create one of the applications I showed you earlier, that psychological assessment application. And this is a staged interaction between a real world clinician on the left and somebody pretending to suffer from PTSD on the right. And the conversation is about The person's on the right, she's pretending that her husband's very upset with her because she's coming home and she's not very responsive. So the husband's complaining about her behavior. And I want you to look at the person on the left. You're only going to see the person on the left. And the person on the right is going to disappear when I start running the video. And hopefully you can hear the video. We'll see that in a second. And take a look at her nonverbal behavior and specifically her gestures.
So your husband wants to be warm and fuzzy, maybe better to the girls, and feels like you and him both feel a little bit like you're a little bit distant compared to maybe how you used to be in the past. Mm-hmm. Is there anything then, besides what he wants, anything that you want to work on, anything that you feel like we could use this time?
Now, one of the things that's happening there is she has a large number of metaphoric gestures. The basic concept here is that metaphors in general, verbal metaphors, for example, attribute physical imagery to the non-imageable, right? So we can talk about grasping an idea as if an idea is something you could actually grasp, right? Now, what metaphoric gestures do is give physical realization to the metaphor. So you can verbally talk about grasping an idea, but you can also represent it with the gesture, right? And you can actually convey grasping the idea without actually even using the word grasping. You can say, that's an important idea to learn, right? And you're using the gesture in somewhat sense independent of the language. Now, the key thing here is that this basic idea of metaphoric gestures is really kind of tied to the notions of embodied cognition. That the way we think about abstract things is in terms of the physical processes and representations and perceptions we have in terms of operating in the world. So we grasp an idea because we grasp physical objects in the world, for example. And in a few moments, I'll be talking about, for instance, you can have an abstract idea and give it physical manifestation as if it's an object right in front of you, and you can throw the object away. And so really what you're seeing both in the language and in the gestures, but not necessarily aligned with each other, is this notion of these underlying metaphors that are using physical imagery to convey often very abstract things.